Hello, good evening all. We will start the session after 2 minutes. Let's wait for others to join. So at 8:02 we will start. Okay. Uh, Hello, good evening. Hope you all are doing great. And before starting the session, all the best for your upcoming examination.
Thank you,
So,
sir.
yeah,
Thank you.
Thank you.
fine, great. So so I think in the previous session, week 5 was mainly discussed. I thought of discussing that also, but anyways, that has been discussed. But if you have doubts in week 5, okay, so you may ask, but towards the end of the session, we will do that. Let's first address the other weeks, 9, 10, and 11 today. And at the end of the session, in general, from wherever you want, if you have any doubts, you may ask. So I am planning to start the session from week 11. I mean, if someone wants to start, I mean, according to your preference only, because I feel week 11 some more doubts are there. But if you say, then I can also start from week 9. Initially, from whichever week we start, that would be addressed a little bit more. So, is there any preference, or should I go with week 11?
Sir, as per your plan, please.
No issues. Okay.
Yeah.
Any other suggestion? Anything you want to say regarding? No one else, right?
You can go your plan.
Okay. Okay, so let's start. Okay, so week 11, we are mainly dealing with complexity classes, and along with that, we actually we read about reduction. That is again a part of complexity classes, and slightly we saw an algorithm called the flow algorithm, which was more about continuation from our week 10s. That not only from week 10, week 11 only, that linear programming models we had, right? So linear programming, we saw that some flow kind of problems. If we have some flow problems, like if you have a network of pipeline, or let's say if you have a supply chain and you want to find the maximum possible flow that you can get, or in that term, in case of supply chain, the maximum possible output that you can get out of your production or out of your chain, right? So there is a bottleneck to that depending upon the weakest link that you have in your system. So these kind of problems can also be formulated in the form of a LPP problem or linear programming problem, but the issue is that's not quite efficient to solve it in a linear programming way. So that's why we also learn about different kind of problem solving, which is specifically to flow algorithms, and we learned the Ford-Fulkerson algorithm. We saw that we did not go into much detailed proof of the things, but it was more of just kind of a observation that there exists some algorithm and we can use it to solve these kind of problems. Okay, like we did not go into the proof of min cut, all those things. So we would be focusing on them just from the problem solving perspective. And very important part is the complexity theory part, because many statements might come as true false, as select the correct statement kind of things. And it is very tricky if you don't understand the concept. So I would be discussing the complexity theory first, and then we would go to, along with it, reductions would also be discussed. Then we would go to the other parts, the LPP, formulation of LPP, and finally network flow. Okay, so let me, before going into the complexity theory, let me just ask this. So can someone just go ahead and tell me what is NP class? What do we? I need the definition, because this is a revision session, and we are mainly focusing on what kind of problems might come and how to solve them. So questions from this complexity theory would come mainly depending upon the statements. So you have to be very precise about the statement. Okay, so what is the exact definition? That should be, you should know that. Okay, so yeah, can someone tell what do we mean by NP class? NP class of problem? No one? Is it? Achha, let's answer in this manner.
Harder than any other hardest problem?
No, that's not NP. That's something else. So my question is, what is NP class? No, I have not started the topic. I just want to ask this question. Then we will start from the basic. Okay, so let me just ask this. You can respond in yes or no. That if I say NP is all sets of those problems which cannot be solved in polynomial time, am I correct or am I wrong?
Correct, sir.
So NP is a set of problems which cannot be solved in polynomial time. You all are saying it's a correct definition. Great. So that means if you are saying that, can I write this statement? Because NP are all those problems which are not solvable in polynomial time. So this directly means this statement, that NP is not equal to P. Correct? Because it is not solvable in polynomial time, that means it's not equal to P. The thing is, this is the question. So that's why I started the session with this question. NP's definition is not at all that. In fact, this statement which we just wrote on the screen, that is yet not proved. Okay, this is yet not proved. No one knows whether NP is equal to P or not. Some of you might have possibly heard about this problem, whether NP is equal to P or not. Or is it equal? Is it not equal? What is it? Is it a subset? None of us know about it. It's under it's a domain of research in computer algorithms, but it's not yet proved. So when you say a statement like NP is a set of all problems which is not solvable in polynomial time, you are essentially saying this statement is correct, which in a way means this statement is wrong, right? And that means you are saying, you are making a you are confirming that NP is not equal to P. So that's not correct. We don't know about it yet. Okay, so if someone says NP is a set of problems which is not solvable in polynomial time, that's a wrong statement. Okay, that is not the definition of NP. Now let's then discuss from the start. Keep this thing in mind, because NP means non-polynomial, so all of us mostly give this definition, but this is very important. It might come. Anyways, so let's see how we are actually classifying the complexity classes. So first of all, there is the normal universe of problems in general, any kind of problem that is there in the universe. Now there are two subcategories. Some problems are decidable and some are undecidable. Okay, so undecidable means what? That is, we don't know what is the solution of it. Even we don't know, given a solution, we cannot be very sure whether it's a solution or not. We cannot even try to solve it, because if we run it, let's say there is a problem, it is undecidable problem, and we try to make a solution of it and run it on a system. The system may not ever stop. Okay, it may not ever stop. It might run into infinity. It would never stop. It would try to. We cannot guarantee that even the system would stop, let alone we will find an answer. So those kind of problems are there. That's not our topic to discuss, but those kind of problems are there. Our main focus is on the other branch, so on this branch, right? Decidable problem. That means we know that there are solutions of this problem. Now let us discuss what is the time that is taken to solve these problems. So depending upon the time which is required to solve the problems whose solutions are there, that is, we know that their solution exists. There can be two further classification. One is intractable and another is tractable. So tractable problems are those problems which can be solved in a polynomial time. So that's why we can also call it P kind of problem. Intractable problems are those problems which belongs to the NP category. That means till date, it should be said in this manner, till date, we could not find a polynomial time algorithm to solve any of the problem belonging to the NP class. Okay, but that does not mean that all problems of NP class can never be solved in polynomial time. I cannot make that statement. Okay, and that's why the definition of NP is not those problems which are not solvable in polynomial time. Okay, so generally speaking, intractable problem or problems falling in the NP class are those problems which takes exponential time. So your time complexity might be n to the power n. some constant a to the power n, like you all have seen 2 to the power n kind of complexity a lot of times. So these kind of problems are exponential problems and they are NP problems. And tractable problems are any polynomial time, n square, log n, whatever. Fine, which are not, I mean, in the power, the variable is not there. The exponent is not variable, intractable, right? If you see here, we can have constant over here, but in exponent, the variable would not be there. The input size would not be an exponent. So those problems are polynomial time solvable problems, not tractable problems. Now these problems are easy to run on the system because as you can see, it takes lesser time. But for very large input, intractable problems would take a lot of time. Okay, so our main motive is how to actually make these problems a little, I mean, let's reduce a little bit of constants in the problem statement of these problems which belong to NP category, and we try to solve them in a some heuristic kind of manner, in a different manner, by reducing the constants a little bit, so as to make them, try to solve them in a lesser time. But okay, so but definition wise, this is the scenario. Okay, now let me come to the proper definition of each of this class, and this is very important. These statements are very important with respect to your program, examination. So what is P class? P class is a set of problem. Okay, a set of problems. Now here you can guarantee a set of problems which can be solved in polynomial time. So this is a valid definition. Okay. Second is NP. Okay. So before coming to the definition of NP, let us discuss one more thing. So first thing is you have a problem and you are trying to solve it. Okay. So let's say you have a graph. Okay. You have a graph or something like that. Let's say some graph like this is there, and you are trying to find the minimum path starting from this vertex. Let's say there is one more vertex there like this, and like this one it is there. Okay, now you are trying to find, this is my start vertex and this is my destination vertex. Okay, and all of these edges have some associated weight, right? And we want to reach from the start vertex to the destination vertex, and we want to cover all the vertices, right? All the vertices only once in the path, right? So this is a very famous problem, like traveling salesman problem. Many of you have heard about it, right? You have to visit all the vertices only once, and then you can reach the end vertex. But the problem is you again have to do it in such a manner. You can repeat the edges, but you have to think about it. If I do not repeat the vertices, can my edges be repeated in the same in the path that I follow? I am not going to tell that. You might think about it. But anyways, that's not the concern. The concern is this is the problem and I want to solve it. Okay. So there you have to come up with an algorithm or whatever, some idea to solve it, right? But so these kind of problems are, we generally say it's an optimization based problem. So that means you have to write the whole code in order to optimize something. That optimize can be maximize or minimize, whatever, depending upon the problem statement. You are trying to find that parameter. And each and every optimization problem can be converted into a decision problem. Now, what do we mean by this statement? Decision problem is corresponding to every optimization problem. I give you a solution. Okay, I give you a solution. I give you the problem as well as I give you a solution, right? And you have to check whether that solution is correct or not, right? Now I say that, let's say A, B, C, D, E. These are the vertices, and I say, okay, so depending upon the weight which is given, assume that all of these edges have weight. Okay. Now I tell you that given this graph and the problem statement that we have to, that's a traveling salesman problem, right? We have to visit all the vertices. So the solution is, let's say A, C, B, D, E. I give you the solution. This is the path in which I should travel. Now your work is to verify whether this solution is, I mean, is it really a solution or is it not a solution? I am just lying. Okay. So the initial time that I discussed only this problem, that was a optimization problem. You had to solve to get the answer. Now I am giving you a solution as well. I mean, I don't know whether it's a solution or not, but I am claiming that it's a solution. Now you have to check for the same problem whether the given solution is really a solution or not. So that is the corresponding decision problem. Okay, and that is a corresponding decision problem, and you would obviously have to write a code in order to check that, correct? So you have to somehow traverse this graph according to this path which I have given and try to come up with a value. Okay, so this value is actually lesser or whatever, depending upon, that's not this question is not in the syllabus, but I'm just discussing that you have to actually verify, right, whether it is correct or not. So like SAT is in our syllabus, right? So let's say I have some x1 intersection x3 union x2 intersection x3, right? Union x1 intersection x4 intersection x3, something like that, anything, right? Any like this, a system of. Okay, let's add a note over here. Let's add a note over here. Like so. Now we have, I mean, I haven't given you an expression, and I tell you that x1 equal to true, okay, x2 equal to false. Assume that, and x3 equal to true, x4 equal to false. So I have also given you this thing, and I'm claiming that this x1, x2, x3, x4 values which I have given, actually when I plug in these values, you would get true as the result. I mean, you would get the result true. So I'm claiming that. So it's a solution. Assuming whenever I get true, that's a solution of the problem. So I say the solution is x1 equal to this, x2 equal to this, x3 and x4 equal to this. Right? What was the corresponding optimization problem? The problem was given this expression, you have to find the value of x1, x2, x3, x4 such that the expression results in a true. That was the optimization problem. Decision problem is what? Now I have given a particular set of encoding and you have to verify whether it's actually giving true or not. So this is the corresponding decision problem. Right? But now in order to check that, what you have to do, you have to put each of these value in the expression and finally compute that I put x1 equal to true, not of x1 is false, intersection x3 is true, so true intersection false, so it would give me false. Accordingly, you have to iterate through the whole expression and solve it, right? So that is one code. Might not be algorithm, but let's, for the sake of logic, let's say that's an algorithm. Right? For difficult problems, you need to have an algorithm even to check whether a given solution is really a solution or not. So these algorithms which are used for checking whether a solution is really a solution to a given problem or not, right? So these algorithms are what we call verification algorithms. Okay, so you are verifying. That's why we call them verification algorithms. And that's it. That's the whole idea. Now let us come to the definition of NP. So I think this verification algorithm is also in the lectures we have used the term certificate, right? The certificate algorithm. So you can also, that's the same thing. Don't be confused with this terminology. Some places it's used verification algorithm. Some places they would use the certificate. Okay, so this is a certificate. So I am giving you a certificate that given these encodings, I mean, this might be true, right? I don't know what would be the result, but assume this is actually true and this is really a solution for this given expression. So then I would say that, yeah, my certificate is the algorithm that I use to actually put this value into this expression and get and see what it results in, whether it results in true or whether it results in false. So that would be my certificate. Okay, and this is that same thing. Certificate is also known as the verification algorithm. So anyways, so that's the concept. Now let us give the definition of NP class, which means a set of problems for which polynomial time verification algorithm is available. Okay, so that's the definition of your NP class. That is, you must have a certificate. Sir has taught the certificate terminology, that you should have a certificate algorithm or a verification algorithm, whatever you want to say, which is running in a polynomial time. This is mentioned in the slide. So please, whenever you are seeing the lecture again, please go through it word by word, line by line, and please pay attention over here in the live session also. So I'm stating this multiple times because in this particular topic, statements are very important. Okay, and it's kind of non-trivial.
Excuse me, sir.
Yeah.
So if a set of algorithm is available which can be solved in polynomial time,
Correct.
then why can that set of problems be solved in that polynomial time? And
No, did not get. It's a verification algorithm. I am giving you the solution. I am not. You are not solving the problem. That's the difference that I explained, right? That first thing is you have to solve the problem. You have a graph. You want to apply Dijkstra on it and find the minimum path. That is an optimization problem. Okay. Now I give you the same graph, and I also give you that between node A and B, this is the minimum distance. Right? I'm telling you that this is the problem statement. You have to find the minimum distance. And I'm also telling you that if you go in this path, I'm giving you a path, particular path. I'm telling that that's the minimum path between those two vertices. Right? So now you have to verify. I am just claiming that. Now you have to verify whether that path is really the shortest path or not. So that time you will, I mean, you did not write Dijkstra algorithm. I mean, you can just apply a simple search and check whether that is actually a minimum or not. Even if you get a single value which is giving a lesser distance from my given distance, then you can claim that yeah, your I can get a path which is lesser than the path that you have given. Might not be that my path is also shortest because I have not solved the Dijkstra. I am just getting one value which is lesser than your value. That means I can guarantee yours is not the solution. So this algorithm, this idea, this logic is the verification algorithm or certification algorithm. Okay, but that is not Dijkstra itself. Dijkstra would give you the least value. So for those intractable problems, right, where solving the problem itself is super difficult, it takes exponential time. But some of those problems which are there, among them, some problems are such that if you give me an answer, I might not be able to solve the whole problem in polynomial time. Okay. But if you give me an answer, then at least I can verify whether that answer is really an answer to that problem or not. And that can be done in a polynomial time. Okay. So you have an answer, you can just back calculate. So this is kind of back calculation. Okay. So that is polynomial time. But itself solving the problem to get that answer, I have not given you any answer. You have to solve it and get the answer. That is intractable. That takes exponential time.
I mean, P is like setting a model, and NP is verifying a model based on some other parameters or set of data.
No, not like, not quite like that. The thing is simple. Just think you. So that's what the definition is. Optimization problem. You have to solve it. Decision problem, corresponding decision problem for that optimization problem is, every optimization problem can be converted into decision problem. The thing is, I am giving you an answer and telling you to verify whether it's an answer or not. Right. So let me just give you this example only. This expression that I wrote. If I tell you to solve it, how will you solve it? I have not given any encoding. How will you proceed to solve it? There is this expression, right? X not x1, x3, whatever. These are OR and these are AND operation, these are OR operation. How will you solve it if and I want the answer to be true?
Plug values which are true.
How many possibilities can be there then? I have x1 to x4.
2.
Not 2. So x1 can be 2, x3 can be 2, x2 can be 2, x4 can be 2. True and false, right? Two values.
Correct.
Now I can have all possible combinations of this. Let's say x1 is true and x3 is false, and x4 at the same time is false and x2 is true. Now I can have another combination, x2 is false, x3 is true, and x4 is true, and x1 is false. So how many possible such combinations are there? That's what I'm asking. Can someone tell?
2 to the power 4.
12.
2 to the power 4, right? You have 4 variables. So every variable can have
Okay.
2 possibilities. So 2 into 2 into 2 into 2. So it's 2 to the power 4. If I give you n variable, which is the generalized three-set problem, that would be 2 to the power n. This is your exponential time. So you just only gave the answer how to solve it. You would plug in value and check it. There is no better way to solve three-set problem. Okay, and if you do that, then the time it takes is exponential, 2 to the power n. So it took you 2 to the power n time to get to the correct value, so that x1, x2, x4, this expression gives you true. But if I tell you, assume this encoding, right? I tell you that x1 is true, x2 is false, x3 is again true, and x4 is false. This is a solution. I am telling you. How would you do it then to verify? Again, same thing. You would just plug and play, right? But this time you have a fixed value. So what you are doing? You are putting x1 equal to true, x3 equal to true, x2 and x4 equal to false, and just evaluating the condition. How much time that would take? Single, only one expression you are evaluating, just putting the true false value. So at most, if there are n variables, even if I consider all of the single operation takes order of 1 time, so there would be n operation, n minus 1 operation, so that would take order of n minus 1 time. In that, I mean, actually it's order of n time. Getting what I'm saying? So when I'm giving you an answer, it's very easy to verify it. Okay, whether it's correct or not. But if I tell you to solve it, then you have to actually go through all the possible encodings to solve it. So this solving to get the solution is a difficult problem. But given a solution to verify that, it's lesser.
So when we are having we are given the values of different variables, then it will be O1 or ON.
ON only, no?
I mean, the values are already given. We need not solve. So basically, expression is.
Yeah, that's what I said. That depends on your interpretation. See, if you think that each of these solution is taking order 1 time, and then you have n variables, so that would take you for each. So let's say, in order to compute this OR operation, right, you have to put it into an OR gate inside the system and solve it. So if I assume that each of these operation is order 1 time operation, and you have n such variables to solve it, then you have to consider that it would be order of n minus 1. That is all, because if you have n variables, then obviously you would have n minus 1 intermediate operands to solve it. Okay, so then we are considering order of n minus 1. But if you say that all of these operations can be run in parallel, if that is the case, then it's order 1 time. But whatever it is, whatever is your interpretation, that's not the worry. The thing is, either way, it is solvable in polynomial time. Okay, but if I ask you to solve it to get the solution, I have not given you solution, that that would take you exponential time. So this thing of plugging, playing, and in this case it's just plug and play. In this case it would be something different. In another problem it would be different. But whatever it is, that verification process, that certification process, that algorithm is a polynomial time algorithm that can be done in a polynomial time. Okay, so the definition of NP problem is a set of those problems which can be verifiable in a polynomial time, or whose certificate algorithm exists, and the certificate algorithm is a polynomial time algorithm. Verification algorithm, certificate algorithm, same thing. Okay, so that is the proper definition of NP problems, NP set. Now the thing is, let us just have a little bit graphical representation of the same thing. So if I draw a Venn diagram of NP and P, as of now it is believed that this is the scenario, P and NP. That is, P is kind of a subset of an NP. Now where we are uncertain about? We are uncertain about whether this P, right, whether this P is a proper subset or not. That means if I say P is a proper subset, so P is a proper subset of NP. So that essentially means P is never equal to NP, right? Because some values in NP would be there that is not in P, right? And yeah, that's the thing. The other thing also, we also don't know that whether this P is such that it might grow and cover this NP total, right? It might grow outside and cover the NP total. So in that case, P would be equal to NP. So which one among these two is true? We don't know. It's not yet proved. So you cannot make a statement like the statement we started with this session. Okay. So as of now, it is believed that P is, I don't know whether it's a proper subset, but it might be a proper subset. It might be a like this subset equal to. We don't know about. Fine. But this is the diagram that I drew just now is what it is believed as of now, that now it's a subset. Now why we call P is a subset of NP? See, the definition of NP is a set of problems for which the verification algorithm exists, and that verification algorithm is polynomial type. That is, given a solution, I can verify. I cannot solve the problem in polynomial time, but given a solution, I can verify in polynomial time. Right? Can I apply this definition to the P class? I know the problem itself is solvable in polynomial time in case of P class. So obviously it is verifiable in also polynomial time. Right? I mean, you can solve the problem itself in polynomial time. So if someone claims that take this is a solution, you can solve it in polynomial time and say, okay, see, this is the actual solution, and depending upon whether that matches with the solution that guy has given, you can tell that, okay, this is correct or this is not correct. Because you can solve the whole problem in polynomial time. Correct? So polynomial time, those problems which lie in the P set, they are obviously verifiable in a polynomial time because they are itself solvable in polynomial time. But NP problems are not solvable in polynomial time, or at least we cannot guarantee that. We don't know as of now. This is the idea till now, that we are not able to solve it in polynomial time till now. Okay, but the verification of those problems is possible in polynomial time. So since P problems can also be verifiable in polynomial time, that's why we say that P is a subset of it. Right? That's the idea. So these two are the proper definition of P and NP, and this is the idea, right? This is, and that's the certificate algorithm we have to discuss. That's in the lecture. I would go to the slides after discussing over here. Certification algorithm, verification algorithm, all those things are done. Now we will discuss two other classes which are NP hard and NP complete. Okay. So what do we mean by NP hard problems? Fine. The idea is, before going to that, let us, we have a prerequisite before going into NP hard. So that prerequisite algorithmic tool which is reductions. Okay, so what do we mean by reduction? So now we are only discussing about the difficult problems. That means those problems which takes exponential time to solve till now. Okay, so the interactable problem or NP problems. That's what we are discussing now. So let's say you have seen a new problem. You are working as a software developer or a scientist anywhere, right? Or academician. So you have been asked to solve a real life problem. Now you don't know. I mean, you are trying to figure out the problem. You are trying to come up with an algorithm, and still you are not able to find some efficient algorithm, which is a polynomial time algorithm. Okay. So at some point of time, you would feel that this is not possible. We cannot solve this problem in a polynomial time algorithm. It's not possible only, right? But in order to make that argument, you have to somehow prove that this particular problem is not possible to solve in a polynomial time. Okay, so I mean, I cannot, therefore I am not able to come up with a proper solution. right? So this is one way of interpreting it, right? And the other way, there is another way. I would come to that later. So in order to prove that, okay, you have to somehow take another problem which is already proved to be a problem in NP class. Okay, so you take a problem which is already proved to be in an NP class, I mean, to be in the NP class. Okay, so you take that problem. Fine. And from that problem, if you are somehow able to reduce it, I would come to the meaning, what do you mean by reduce it? I would come to the description for that. But somehow, let's say, if you can convert that problem now, that the problem that you took, if you can convert that problem into your problem. Okay, you took a problem which is already in NP class and you somehow converted that problem into your problem. Now, how do we convert that? What do I mean by convert? These problems are totally separate problems. How can we simply convert them, right? So the thing is, so what we do is, let's say this problem, which problem A, there is one problem A which is already believed to be in the NP class. Not believed, it's in the NP class. So this problem A would have some solutions, right? Maybe it took exponential time to solve, but obviously it has solution because we know these are decidable problems. Whether NP or P, these are decidable. So we know they have solutions. Okay, but it took a lot of time to calculate that. So let's say it has a solution, and that solution is, let's say, A. Okay, and there is another problem B, which is my current problem, which I am trying to solve. Okay, the thing is, let's say I have given the output OA inside the solution for this A problem, and I got a sorry, not output. What I'm saying, I have given an input IA, right? IA is just an input to the problem A, and it took exponential time, but it gave me the output as the solution as OA. So IA is the input, OA is the corresponding output, right? In order to convert A problem into B problem, the thing is I have to map each input of A problem into some corresponding input of B problem. Now this alpha, let's say this is alpha, so alpha is an input to B problem. Now alpha is totally following the semantics of the B problem. Okay, but I somehow managed to get a logic of saying that these components of the input of A problem, I can relate it with the B problems component, right? Input of B problems component. Okay, so if I can map the input of A problem, every input of A problem into a corresponding input of B problem, right? If I can do that, so then I can say that this output which I get out of A problem, and let's say some output of B problem is beta, then I can also say that these outputs are also, I mean, relatable, mappable. Okay. So the idea is, if I can, so this can be also used. This is actual reduction. This process is what we call reduction. If you can somehow convert a problem into another problem by changing every input of the first problem in a way related with the input of other problem, right? You are just relating it by some logic. Okay, and then you are claiming that, okay, that's my logic of relating the input of A problem to B problem's input, and since I have done that successfully logically, that's why I can also claim that the output of A problem is also relatable to the output of B problem. Getting the point? And that's how, if you are not able to solve A problem but somehow able to solve B problem, then you can simply say, without solving the A problem, by simply seeing the output of B problem, what might be the output of A problem. So this has been discussed in detail in the lecture by relating the flow algorithm with the bipartite matching. So I mean, it's not directly required because we would not be asking you proofs in the examination. But the idea is that in the lectures are as discussed, right? How we map the flow algorithm to bipartite matching. So you can do that. So that is simply the same thing. You are applying the flow problem, sorry, the Ford-Fulkerson algorithm in order to find the bipartite matching. So you have not solved the bipartite matching. but you are able to relate the input of flow algorithm and able to relate the input of the bipartite problem. And then you are able to claim that if the solution of my flow is this, then that is related in this logic with the solution of bipartite, and hence the answer of bipartite is this. Okay, bipartite matching. So that is the whole idea, and that's what we call reduction. Okay, you might not go into the details of it, just understand these things because you should be able to pick the correct statements from the questions. Okay, just understand the concepts. Okay, so that is point number one. So this is what we call reduction. Now, there is a little bit interesting point over here that when you are trying to convert a particular problem into other problem, you are applying some logic, right? And then trying to convert it into another problem. So I have converted A into B. Okay, so this needs some extra work, right? Some extra work. Right. So since I had problem A and I did some extra work in order to convert it into problem B, then I can say from the outside that B is a much difficult problem to solve than A, right? Because I had A, I added some extra complexity, some logic, whatever, in order to convert it into problem B, right? So therefore I can say that B is more difficult than A. I'm not claiming NP and NPP and nothing. I'm not claiming anything. I am just claiming that if I reduce, if B is reduced from A, then this statement. This is very, very, very important. Okay. If I take a problem and from that problem I reduce it to another problem, then the problem into which I reduced my real problem, that is a more difficult problem to solve. So in this case, if I take A problem and try to convert it into B problem or reduce it into B problem, okay, we say it reduction, but I mean, if you want to take the literal meaning, we say it's reduction, but reduction doesn't mean that you are reducing the complexity. Actually, you are increasing it because you are putting some extra work in order to convert A into B. Okay, so if B is reduced from A, then B is a more difficult problem than A. So now let's come back to our story where you have to prove that given a problem, it's a difficult problem to solve, it's a NP problem to solve. And that's why you are not able to come up with a polynomial time algorithm of it. Fine. So if you take a problem which is already in the NP class, right, and convert it into another problem. So my alpha is in NP class, and I reduce this into beta. Then obviously, according to this logic, I know beta is more difficult, right? Now, if beta is more difficult, that means if alpha itself was in NP, beta is more difficult than that. That means beta is obviously also in NP. Right? It is also a difficult problem to solve. Okay. Now, let's say I say alpha, I have reduced from alpha to beta. Okay. And the information given to you is that beta is a difficult problem. See, this is the trick. Please pay attention over here. Case 1, case 2. Let's analyze these two statements. Both case I have taken alpha and I have converted it into beta. Let's delete all these things. The basic concept is clear. Fine. Same thing, I am taking alpha and converting it into beta. In this case, it is given that alpha is NP. In this case, it is given beta is NP. Nothing is told about beta over here. Nothing is told about alpha over here. Okay. The question is, what can I tell about beta in this case? What can I tell about alpha in this case? Can someone tell?
In first case, beta is even harder.
Correct.
And in the second case,
even harder means I want to know the class. NPP.
NP hard.
NP, correct, NP hard. Actually, that's correct, but let's see, yeah, correct, NP hard. Let's see, right. I would come to this hard word a little bit later for others also, those who have doubt. But you can, as of now, consider, yeah, it's NP hard. Yeah, and the second one,
So beta is NP class, so alpha can be, I mean, not less harder than NP class, so it is NP only.
is it NP? Or
Is it
P?
like, sir, any algorithm is going to be hard? Like any algorithm is going to be NP hard if beta is in NP, and from alpha we can get beta, then any algorithm alpha is going to be NP hard.
In the second case, you are talking that alpha is NP hard?
Yes.
Okay.
In second case, no. In second case, I'm saying that any algorithm is going to be NP hard.
Any
all
algorithm NP hard?
It means like all algorithm.
See, what I'm asking is, what is the complexity class of alpha in the second case? Can I tell anything about it? Is it NP? Is it P? Or can I not tell anything about it? That's the question.
Hello, sir.
Yeah.
It can be P or NP.
Correct. So that's the answer. In second case, I cannot tell anything about it. It may be P, it may be NP. That depends on the reduction algorithm or the certificate algorithm.
One doubt, if it is P, why do we go for reduction? We will rather do it, right?
Sorry?
If it is P, sorry, why do we go for reduction? Only because it must be NP.
Correct. So logically that's true, but here I'm asking you from a, question perspective, that if it's given that you have an algorithm, you have a problem alpha and you reduced it into beta, and let's say beta is NP, then the question would say alpha is NP, alpha is P, alpha we cannot say anything about. Three option is there, which one is correct? So from question perspective, I'm telling, from concept perspective, you are correct. If a problem is NP, then only we will think about reducing and all this.
Okay.
Okay, so yeah, so concept perspective, that is already solved, that I discussed, that you as a developer or an engineer or a scientist or whatever, you are trying to prove that a problem which is given to you, you are not able to solve after some days, and in polynomial time. Solve means in polynomial time, right? And you are thinking that there is no possible algorithm to solve it in polynomial time, so how can you formally claim that? So then you use reduction. You take an algorithm from the NP class, right, and then try to map it to your problem. Sorry, not P. Your problem, and you say that I know that if I reduce this reduction, so if I reduce a problem into another problem, in case my problem, so my problem is much more difficult than the problem with which I started, right? So that's the concept that would always apply. This line, that after reduction, what I'm getting, that is more difficult to solve. So if I have already taken a difficult algorithm to start with, and I have successfully mapped it or reduced it to my problem, then I can claim that my problem is much more difficult than this problem. And this problem has already proved in literature to be in the interactable class, NP class. So there is only exponential problem algorithm to solve this problem. So you cannot expect me to solve my problem in better time, because it's actually harder than a problem which is in NP class. So that was the conceptual viewpoint of this. This is more related to your examination, right? So alpha to beta in both cases. In this case, it is NP hard, obviously, because of the same logic. This is the same logic over here. But the other way, if I tell you that this is NP, then we cannot tell anything about alpha. It can be P, it can be NP. Why? Because I don't know what is the reduction algorithm. If the reduction algorithm is exponential, then alpha might be P, because alpha is P, but my reduction is taking exponential time. So that's why beta is becoming exponential. But if the reduction itself is polynomial, then might be alpha is itself also NP. So basically the answer should be, if this is the case that has been given to you, alpha to beta reduction, beta is NP. What about alpha? Answer is we cannot tell. Okay. So So statement 1, statement 2, please keep these two statements very important. It's very, understand it. If you have doubt, ask it. Okay. If every one of you got it, then we would proceed. Is there any doubt regarding this reduction and conversion?
Yes, we can proceed.
Sure. Okay. So NPP.
And if it is given in statement 2 that the reduction algorithm is polynomial, or I'm sorry, something is stated about reduction algorithm, then can we say about alpha?
No, and most probably that would not be stated because that also is not a proper statement. Nothing is proved over here. So we can only ask you questions, not only we, I mean anyone can, in this topic only those questions can be asked which is proved. Otherwise we cannot frame question, we can get into discussion. So that's why statements are important, and most probably nowhere in our course it's obviously you would not get anything about the reduction algorithm, and I don't think anywhere, I mean questions can be framed, I mean a lot about reduction algorithm and its conclusion into the final problem, because again we cannot make it a statement that if reduction algorithm is polynomial then always alpha would be NP. That also we cannot say. Fine. Anyways, so basically the thing is these two things are important, that if alpha is NP and you are converting alpha to beta, beta is definitely NP, NP hard actually, as you said correctly. And if beta is NP and I have converted again from alpha to beta, then I cannot say anything about alpha. Only twist that's possible is, and that you have to think, I would not tell, that is if the same question is stated along with the information. In case 1, alpha is NP, not NP, sorry, alpha is P, and in case 2, beta is P. Now we have given information regarding NP, correct? But another twist to this question is I am giving you information in terms of P. So I say you convert alpha to beta, but alpha is P, and in the second case, same thing, alpha to beta conversion, but beta is P now. Okay, so wherever NP was given, I am saying P is given. Then what should be the answers? Okay, again, it can be P, it can be NP, it can be, we cannot decide. So yeah, that you have to think. Depending upon this concept only, if you keep in mind this concept, right, then you would be able to answer all of this. Fine. Yeah, you want to ask something?
No. I mean, in the first case, it can be like NP or NP hard. We can't say.
So I would not say that.
If alpha is P.
You have to think about that. Okay, but it's answerable from this. That's there is no more twist in this. Just if you apply this, it should be answerable. Okay, now this NP hard word came actually. So what is this hard and complete? And that would end our discussion with this NP process. So when we are converting alpha into beta and alpha is in NP, we stated beta is harder than alpha. That concept is done. So those problems which are harder than all the problems in the NP set. So I drew over there the NP set, right? So let's say I have many problems like this, multiple problems are there. Okay. Many problems are there. So let's say these dots represent each of the NP problems. Now let's say I come up with a magical problem, right? Let's call this problem M, magical problem, such that I could map the input of all these problems over here, the input of all these problems over here into the input of M. So we discussed that if you can successfully map the input and output of a problem into another problem, that's essentially a crude definition of reduction, right? It's not the axiomatic definition, and that is not in our course also, but that is actually the definition of, I mean, the overall understanding of reduction. Okay, so if I can map the inputs into the input of M problem for all the problem belonging to NP class, so that is basically you are able to reduce all the problems of NP class into the M problem, this M problem, right? You are able to reduce it into M problem. That essentially means this M problem is harder than all the problems of the NP class. Okay, and these problems which are harder than all other problems of NP class are called NP hard. Okay, so how question might come? The question might come in this format that NP hard problem. Let's say 3 statements are given, and one is asking NP hard problems are those problems which are polynomial time verifiable. Okay. Second option is stating that NP hard problems are those problems which are not solvable in polynomial time. Third statement is stating NP hard problem are those problems which are hardest among all the NP problems. That's it, simple. On the basis of this, you have to answer, and it might come in an MSQ format. So you have to check all the correct definition, right? All the correct properties of a particular term. Fine. So, by the way, since we are on this topic, so when I said the option 1 is NP hard problems are all those problems which are verifiable in polynomial time. Is that correct for NP hard or is it not? What do you think?
Yeah, correct.
Could be or couldn't be.
No, the verification is always in polynomial time, right?
Yeah, verification is always polynomial time for NP class.
NP, yeah.
Yeah. And what I said just now, the N problem is a problem which is harder than all the problems of NP. Correct? Because you can convert all the problems of NP. Convert means reduce. Convert, reduce, map, whatever you want to say. The idea is you should be able to map the input of this problem into the input of N problem. That's the idea. Fine. So when I say you are able to reduce all the problems of NP class into this M problem, that means M is much harder than all these problems in NP. If M is a more difficult problem, then it might also be possible that the verification algorithm of M is also exponential, right? Because it's super difficult problem. It's harder than all the problems in NP. So it's a very difficult problem to solve. And therefore, it might be, it is not always, right? I'm saying it might be so difficult that even the verification algorithm for this problem is exponential. Okay. So for NP, verification is polynomial time. That is fine. But now I'm dealing with a totally different problem. This problem is a much more harder problem than all the NP problems. And that's why I'm able to reduce all NP problems into this problem. Fine. So these problems which are there, we call them NP hard, and since this is much more harder, it might be possible that the verification algorithm is also exponential time. That's why NP hard problem is never stating that the verification is a polynomial time algorithm. There exists a polynomial time verification algorithm for NP hard problem. Okay, the definition of NP hard is NP hard problems are all those problems which can be obtained by reducing from all other NP problems into our concerned problem, right? So if you can reduce all other NP problems into this problem, then that's the NP hard problem. That's the only definition of NP hard. Okay, now we will add this verification feature. Now when we say now NP hard problem is done. Okay, now we say NP hard is there, plus it is harder than all the problems in NP, that is fine. But now I say that the verification also, let's say some problems are such that we can convert all NP problems into this problem, and that's why it is NP hard. But I see that even though it is NP hard, but still I get a polynomial time verification algorithm. Polynomial time verification algorithm I got. In that case, when it is NP hard, plus I get this extra feature of polynomial time verification, then we say it is NP complete. And as you can observe that since it is plus this extra feature of polynomial time verification, I know polynomial time verification is the definition of NP class, right? So that means what? That means NP complete must be residing inside the NP class. correct? Because so if I redraw the diagram, let me just state whatever I said, then I would redraw the diagram and then I would just make all the summary points. So any problem of NP is convertible into a single problem. That problem we call NP hard. That is the hardest. Since it is hardest, and it might not be a single problem. There are a family of problems which are NP hard. Okay. So since these problems are harder than any NP problem, fine. Therefore, it might be the case their verification algorithm is not polynomial time. That's why NP hard problems might not have a verification polynomial time verification. Fine. But again, I see that some problems are there which are actually harder than all NP problems, and I can convert all NP problems into this problem. But I also can have a verification algorithm for this problem which are polynomial time. So those problems we call NP complete problem. Okay, but since I know that polynomial time verification algorithm is the definition of NP problem, and I am claiming NP complete problem also have polynomial time verification, that means NP complete problem must reside inside the NP. So if I consider this problem as an NP complete problem, that means this problem is harder than all other NP problem inside, I mean all its colleagues, all its friends inside the same set, right? And also it is residing inside NP itself. That's why it is verifiable in polynomial time. So if I redraw the diagram, then how should the Venn diagram look now? This is my NP class. This is my P class. Some problems are such that I do not have a polynomial time verification, but I can reduce all NP problem into this problem. These are my NP hard problems. Which part? Only this part. I do not have verification algorithm, right? So that's why I'm not putting it inside NP. Only this part is NP hard. Fine. Let's say with NP hard property, I also have the polynomial time verification. Now, since polynomial time verification is a property of NP class, so I have the intersection, right? I have the property of both NP hard as well as NP. This is this region, the intersection. So NP hard, NP complete, NP, and P. This is the basically, if you have this diagram in mind, and whatever we discussed, this part, right? This part, if you keep this thing in mind, I hope all the statements you will be able to answer. Any doubt?
No.
Great. Fine. So that was it regarding the NP and all this thing. Now we will go to the LPP and flow. So, I mean, there is not a lot of thing to discuss over here because this totally is dependent on your understanding of the comprehension which is given, right? So you have to read it in the, I mean, we would not be able to, sorry, we would most not be asking you to solve a simplex problem, right? But questions might come in the form of, sorry, just give me a second. Yeah, question might come in the form of a comprehension is given just like this, this production planning right here, Sarah discussed the statements, right? So like that statements might be given and you have to most probably 4 or 5 options would be given that which of the following options correspond to a proper formulation of the constraints according to the story given, according to the comprehension given, right? So every LPP problem will have 2 things, right? First would be a set of constraints which you have to follow, and then you would have a optimization function. So what I mean is yeah. So here you see you have a set of constraints, right? Constraints means you have to follow these things that, I mean, all of these are greater than 0, 20 into wi plus oy equal to xi. So these constraints are formulated simply on the basis of the comprehension given. And second thing in the LP problem is the objective function or the optimization function. That is whatever you have to minimize or maximize. Either if it is cost, you have to minimize. If it is profit, you have to maximize. So depending upon what is asked, so you have to form the expression for your objective function. That is the thing for which you are trying to maximize or minimize it, and the constraints. Okay. So that would be asked just to correctly choose the proper constraints or the proper optimization function or the objective function. Fine. So is there any specific doubt in any of the problems which is discussed in LPP? Then I can discuss that. Otherwise, there is not a lot of conceptual thing to discuss. Is there any specific problem you want to be discussed? I mean, over here, let's say this problem or the bandwidth allocation problem. If it's fine, then I would not consume time on this.
No, sir, it's clear. The difficult part is in max overflow and minimum cut like things.
Yeah. So I'm coming to that then. Fine. Actually, this is a bit more easier. What you have to do is, I mean, in terms of formulating the constraints, the network bandwidth is easier problem to solve. So at least be confident with this question. I mean, this concept. Network flow. See, so network flow, the thing is, first we will, I mean, so this has been discussed very briefly, not into the detailed way of solving it or detailed way of proofing it or anything, just as a introductory kind of thing. So question, if it comes from network flow, then it would directly ask you to just calculate the maximum flow. And that would also be for not a very difficult graph. For a simple graph only it would be given. If you want to discuss the process, so the process is very simple. So this is a bit big graph to discuss about it, but let's say, okay. Okay, so let me just open the Corman book. Here already the diagram is there. Just a second now. If some of you have any doubt regarding the maximum flow, although simple question would come, but if you want to understand it properly, please refer the Corman book. I mean, that's the best source for this algorithm. It explained in very detailed manner. You can refer.
Sir, can you share the link of this book, please, in the chat box?
It's on the website. I'm sorry, not on the website. You can just go to Google and write Corman PDF. It would come.
What is the name, please?
Corman, C-O-R-M-E-N.
Okay.
Okay. And I mean, this book is just for your future reference also. So many of you might know it because this book is basically, so as they call it the Bible of algorithms or the main book for algorithms. Okay. So great book. You can refer that for any of the problems. But there are not a lot of solved problems. So it's more of a theoretical approach to how to discuss this algorithm.
So where is this? You can just get it from the net.
Sorry?
Where is this book available?
I mean, book available means?
No, is it? You can search in Google or
Yeah.
okay.
If you want to buy it, you can buy it, but you can get it. Oh, that was confusing.
If we can take graded assignment 11, questions 3, 4, 5, then it will, and try to solve them.
Okay,
That will help to clear the concept also.
fine. We'll do that. Let me just discuss this. Where did it go? I see it was 700. Okay, finally, yes. See, so I would go to the graded assignment, but before that, let us just have a brief understanding of how to solve this problem.
Sir, it is on page number 729.
Page 729, no? But the thing is, I don't know why. Why?
No, sir, page number 729 of PDF, not that book.
Okay, anyways, okay, let's just start this time. I just want to discuss the approach and then maybe we can go to the graded assignment. Okay. So this is your source vertex, this is your destination or target vertex, whatever. Okay, and let's say I'm arbitrarily putting some value. Right? Okay, so all these edge values are basically the maximum capacity that can flow through these edges. Okay, and the direction is given. Now, how the Ford-Fulkerson algorithm basically works, we would not go into the detail, the conceptual things and all, just the basic how to try to solve a problem. Even I don't think this kind of graph would also come, but even if it comes, but anyways. So how to solve it basically is, what we do is, first you would take any of the random path. Okay, you would take any of the random path in order to reach from the source to the destination. So that's your step one. Take any of the direction, that doesn't matter. It matters from the performance point perspective, but we would come to that later. So let's say I take this path. Okay, so this path I would take this path. Okay. Yeah, so I go along this path like this. Okay, then let's say I go along this path, that's straight one. Fine, and then I simply go in this way. Fine, so that's my idea. That's sorry, that's my path. Now, when you are going from source to destination, this following this given path, then you have to check that in this path, what is the bottleneck capacity? That is, I have 12 over here, I have 8 over here, and I have 12 over here as well. So whatever I pass from here, right, 12, and I would only consider this path. Huh? Whenever you are considering a single path, only see that. Do not consider other edges and all other networks and all those. Simply see that what I am seeing on this path. I see that 12 is there, 8 is there, and 12 is there. Right? But I cannot pass more than 8 from this edge, and that's why even if I pass 12 from here, I mean, it would be a bottleneck, right? I cannot pass more than 8. So you pick the smallest possible capacity in the path that you have chosen, and that much flow you actually allocate to all the path, all the edges on that path. So I see the minimum, did I say maximum? I mean the minimum capacity. Okay, you take the minimum capacity among all the edges in the path that you considered and simply allocate that much flow to all the edges on that path. So I allocate 8 over here, I allocate 8 over here, I allocate 8 over here. Right? And all other edges have 0 flow as of now. There are no flow on those edges.
Sir, could you explain this concept once again?
Yeah, so it's simple. Just take any one of the path that from the source to destination. What's important is it should be from source to destination, from S to T. Take any one of the path. You should be able to reach the destination from the source, right?
So, sir, in theory, we could take the path that is 12, 9, and 4 as well, correct?
Anything.
Right, sir.
Anything. So you take any of the path and then you have to pick the minimum possible capacity, the bottleneck capacity on that path. So in this path, I have 3 edges, and one is 12, another is 8, and the third one is also 12. So if I number
Right,
it,
sir.
correct, A, B, C, D, and that is S and T. So AB is the bottleneck because that's the minimum possible capacity. 8 is the minimum possible capacity because SA is 12 and BT is also 12. So therefore, I can only pass the minimum bottleneck capacity, right? Even if I pass 12 from S to A, considering only the path S to T, do not consider the rest of the network. Do not, when you are considering a particular path, forget about the rest of the network. So if I only pass S to A, if I am able to pass A to B only 8, whatever I pass from S to A, that would not sustain if it is more than 8. Correct. So you pick the minimum capacity and allocate it to all the edges on the path that you are considering. In this case, that is 8. Right. So that I did. After that, what is the next step? Now this is the beauty of Ford-Fulkerson algorithm, that if I have taken the flow to be 8 on the edges, I mean as of now, I might even get a more amount of total flow in the network, even by reducing some flow from one of the edges. Now we would see that why that is true. But before that, let's see what is the next step. So the next step is I have a possibility that even if I can reduce the flow in one of the edges, I might get a better flow, the total flow. That is the only concept. I have not done anything to represent that. That's the thing that we should keep in our mind. That this does not mean if I can saturate all the edges, I would always get the maximum flow. No, because there are some edges in the opposite direction as well. So if you saturate a particular edge, that might push some water into another edge, and that edge may be directed in the opposite way towards the source. Right? So if you put lesser value in an edge which is directed towards the source, you might get a better flow towards the destination. So that is the conceptual idea. But how to actually do it? Let us see. So because of this idea, what we will do is we would make something which we call the residual graph. Sorry. Which we call the residual graph. Now, what is residual graph? So I would be making the residual graph on this graph only. Okay, but for your proper understanding, you can also see the subsequent graphs, right? So you should actually in the first time you should always make the graph separately, the residual graph. So what do we mean by the residual graph? So the residual graph means, if observe this graph, can you all see my cursor? now? No,
Not right now, sir.
Okay, great.
No,
sir.
Okay, fine. Can you see now?
Yes, sir.
Yes, sir.
Okay. So I have a flow directed from S to A, that is 8 in the original graph. What I would do is, in the residual graph, I would just reverse the direction of the flow, and that allows me to actually check for path such that I might be able to reduce the flow in one way and increase the overall flow. That means what I would do is, okay, so let's draw the residual graph separately, at least for the first time. What that means is, from S to A, I would draw one edge which is in the same direction, right? From S to A, I am drawing the edge, which gives me the residual capacity, which is left over. How much is left over? I have passed 8 out of 12. So
4.
correct. So mark 4 over here. And we discussed that there might be a possibility that if I reduce the flow in a particular edge, we can get overall flow which is better, right? Because of the logic that I just gave, that some edges might be directed some other way and it might actually push water towards the source and to make it a lesser value. Okay, so that's why there is a chance of reduction, and that's why what I'm doing is, this is the trick of Holt-Fulkerson algorithm, that I would add an opposite edge corresponding to the flow which I just added. I mean 8 in this case. So just bear with me, you would understand what's happening. So this is the first vertex pair. The second is, I again draw in the same direction I would draw for the residual capacity. What is the residual capacity over in this edge? It is 0.
0.
Just accordingly, we would draw the opposite thing, which is 8. Same way I would draw another edge over here according to the residual capacity, which is
4.
done. Fine. Now, in fact, I can also use a graph which is in the lecture, that is also easy. But anyways, so let's have the concept from here. Then we might go finally solving.
Sir, please explain it again. This one.
This
4,
one?
0, 4.
Yeah, I mean, we did not do anything. So just you should add the residual capacity in the same direction. So
Okay.
here the residual is 4, right? 12 minus
Yes.
8 is 4. So I added that in the same direction. And since I have a chance that if I reduce the flow in one direction, therefore I am adding, I'm adding an option for myself to reduce the flow just by reversing the flow direction. All right, I am not reducing anything. Okay, this is not the solution. This is just a way to approach the solution. Okay, so I just have a chance. That's why I oppose the direction. Okay, all other edges which were not touched in the first iteration, you keep it untouched. No changes, just keep it untouched.
Sir, is there any specific way to choose that directions? Or we can choose arbitrarily any directions?
Which direction I did not get?
Actually, if I want to choose SC, D, B, T, can we choose that one?
You can choose anything. Only thing is that decides how much time you would take to converge to the solution. You would get the solution in either of the case. Only thing is that would decide how many iterations you have to make. The first initial choice of path that you take, that decides how many iterations you have to make to converge to the solution. I mean, to basically solve the problem. Okay, and that there is no specific rule to do that. There is no specific algorithm to decide that. And that is the only disadvantage of Holt-Fulkerson algorithm. So what's more important with respect to Holt-Fulkerson algorithm is, from your exam perspective, is does it always give gives a correct result or not?
No.
Is it? Yeah, no, it will always give you the correct result. Okay, it would always give you the correct result. The problem is, if you choose a bad initial path, it would take a lot of time to give you the correct result, but it eventually will give you the correct result. And if you choose a good initial path, right, like I chose SABT, you choose SADBT or SADT or whatever, you choose a path which is better, then it would take lesser number of iterations What iteration I have not yet discussed. Let me discuss that. So it would take you more time to basically reach to the solution, but in either of the case you would get the same solution, and that is the correct. Okay, so it always gives you correct solution, but it would take more time if you choose a bad path, and there is no proper way to choose a good path just by seeing the graph.
Okay.
So that's why I am saying even if a question comes, it would not be very difficult. So okay, so let's come to the iteration. What we are doing. So you add the residual edges in the opposite way, and you in the same way, and the flow that we have passed till now in the opposite direction. And you would do that only for the edges that you have considered in the first path that you have chosen, not for the other edges. If you see in my these other edges, right? I did not do anything with all this. So this is my first residual graph. Now that after constructing this residual graph, what you have to do? I mean, it's very easy to do that. I mean, I'm explaining it, that's why taking time. Otherwise, it's just common sense. Right? Just do it to take 1 or 2 seconds. So after that, what you would do? Right? Now you can consider any other path. Okay. Consider, not can, you should consider any other path in the residual graph. Right? Now, other path means, let's say I consider the from S only. Always S. Huh? You cannot consider arbitrarily, you have to reach to T from S. Now you find the path in the residual graph, and this path is what we call the augmenting path. But anyways, now you find the path in the residual graph. Okay, just tell me another path in the residual graph. It should be a different path. Huh? Tell, yeah.
SCDBT.
Okay. Great.
SCDBT.
Okay. So S A D B T. So this is my another path. Fine. Do not go for the same path, otherwise it's logicless, right? Doesn't mean anything. Now you take another path, but this time you take in the residual graph. Fine. This time you take in the residual graph. Now let us see. What is the next step that has to be done? So my path is marked in red. Now what you will do is, this was your original graph, right? This was your original graph. This is your residual graph. Residual graph is a tool to reach to the next possible better flow. But that's not exactly the flow, right? Try to understand this. When I said that I'm reversing the edges, I actually did not reverse the flow, right? I am just trying to enumerate all my possibilities to calculate the next maximum flow. Original flow, if you say the current flow in the graph, that would always be the flow which is there in the original graph, not in the residual graph. Residual graph, I constructed these back edges so that when I find the new path in the residual graph, then I might pick one of these back edges in the new path. And when I pick a back edge in the new path, that essentially means I'm reducing the flow in the original graph. That time I would reduce. So what I mean, let me just do that, you would understand. But you would not understand this in this iteration, because actually I have not used a single back edge in this path. But anyways, let us go with it. So I've taken the path SDBT. Okay. Now your next step after taking the path in the residual graph is, you need to see on your path that you have taken in the residual graph, which edges are along the same lines as the path which was there in your original graph. Okay, so if I consider in the residual graph I have taken SA. Is this SA edge directed in the same direction in the residual graph as in my original graph?
No.
SA edge.
Yes.
SA edge is this direction, right?
Yes.
SA is in this direction, correct? I have taken, this is my path, SA like this, SA DBT. Sorry, SA DBT.
The weight has changed, so okay.
Yeah. So it's in the same direction. So what you would do is, since it is in the same direction in over here, you make it 8 plus the capacity over here. So whenever an edge is in the same direction in the residual graph, after you pick the path in the residual graph, you choose each edge and compare the direction of that edge with your residual graph's path to the original graph's path, where you have already added the flow. Fine. Now you add it if it is in the same direction, you subtract it if it is in the opposite direction. Okay, so now 4 is in the same direction, so I would add 8 was already there, so 8 plus 4, 12. Fine. So what is the next stage? This is my next stage. Let me just delete this red color from there. I don't think I took the flow algorithm open session, or I mean the concept discussion session. So initially how it has been discussed, I mean basically you apply the flow and then go with it, right? Was the residual graph discussed?
No, I guess.
Fine. Okay. Actually, we have not gone into that also, because that's why I'm saying sir has also discussed it just for giving you an idea of how that there exists something like this. And most probably the question that would come in the exam, if you just pay attention to the graph, you would be able to solve it by brute force. But it would come, so you should be able to answer it. So anyways, so here it is in the same direction. I added 4. Here it is in the same direction or not? Now see, one problem over here is I have not added any flow in the original graph in this edge, right? AD. Consider the edge AD. Here I am seeing 9 is the flow, right? I have considered 9 is the flow, but here it is actually 0 because I have not added anything. So if you are getting confused, let me just write these things in this format. It is 0 by 4, 0 by 9. All these flows are 0. 0 by 8, 0 by 4, 0 by 10, right? These were also zeros, but we have added a 4, that's why it is 8, 10, whatever. Okay. So now I see that here 9, I'm taking a 9 capacity, but here it was actually 0. And it is also in the same direction. So how much will I add over here? 0 plus 9. Because in the same direction, so I add that. So 9. So what is the next one? Next one is this particular line. So it is D to B 10. And again, here it is 0, same direction, add 10. So I add 10 over here.
Sir,
Yeah.
could you please repeat from the age AD?
AD. So it's the only thing is, so when we wrote this blue colored in this graph, blue colored values in this graph, those were the capacities, those were not the flow. But whatever I am writing in this graph, right? So this is basically, if I'm going in this path, that means I'm adding a flow of 9 because I've chosen this path. Now here it was 0, right? Initially it was 0. I have not chosen this path initially. It was 0, right? So what did I do in this edge? What did I do? Initially it was 8. It was 4. The flow was 4 over here on my path. So since it is in the same direction, so I added 8 plus 4, which is giving me 12. Accordingly, over here I see 9 is the value, right? And here initially it was 0. So I added 0 plus 9, which is giving me 9. So I write 9 over here.
In the residual graph, we had this back edge of flow of 8.
Where? This one?
Yes, so that is what we are adding back to 4.
No. Where we are adding? We are not adding anything. 8 was already there in, so that's what I said. Residual graph is just for your, it's not a flow, it's just a tool to go to the next flow. So what I mean is, did you pick this edge in the path from S to T in the residual graph? You didn't,
No.
right? So if you didn't pick it, you do not have to worry about anything. So you only consider those edges which you have picked in the path in the residual graph and see whether the corresponding edge in the original graph is directed in the same direction or not. If it is directed in the same direction in the original graph, then whatever is the flow in the original graph, which you have already written, with that flow you add the value which is there in the residual graph for that edge. If it is directed in the opposite direction from the original graph, you simply subtract it. Just so up till now what we have done, this is same direction, 4 was
Clear,
there,
sir. Now clear.
add 8 plus 4, 12. This is the second path, which was 9. Here I had 0, here I had 0, so I added 9 because it is in the same direction. Then next path is this one, which is 10. Again here I had 0, so I added 0 plus 10, which is 10. Which is 10. What is the next one? Next one is 4. Huh? Is it in the same direction or opposite direction? In the original
Same.
graph.
Same.
Add 8 plus 4.
12.
12. So let me write 12. Fine. So this is our new flow.
So dB should be 9 or 10.
Which one?
dB.
dB is 10, right? Oh, so you are not able to see it.
No.
There is one line.
No, I'm saying we have AD is 9, so dB should be 9 also, right? 9/10.
No, I'm not getting.
We are having 9 from AD, so that is going to.
Have I? Yeah. So have I actually considered the flow from here? No, right? I have not. So this is the algorithm. I have not stopped. I have not completed the algorithm, right? We have to complete the iteration, then we would see what's happening. Okay. It might also come from top. I don't know. It might be coming from any of the places. So when I complete it, you would see. Fine. So then I get over here. I added the flow which is 10. Assume I have added the flow 10 over here, and 12 has been added over here. Okay. So that's done. Now, I mean, everything might change. Even these things would change. I am not sure about what would happen in the next iteration. But this is basically the flow right now. That's why I said that this takes a lot of time to iterate through unless and until it's a special graph which takes a less iteration. But you would have to iterate through it multiple times. But the process is this thing. The correct process is this. So anyway, so this is my new flow. 12. This path I did not consider. Okay. Yeah. So this is my current new flow. You do not have to think about the logic if their values are correct or not. Just you have to proceed with it because we have not already relaxed. Gone through all the paths. So now again you would draw the residual graph corresponding to this new graph which we got. We have changed the flows, right? So again you draw a residual graph which is corresponding to this graph. I just want to come to a stage where I would be able to discuss that one package is actually contributing. And then we can go to a simpler example. But anyways, so now the flow is 12 in this direction. So I would add an opposite direction 12 in the residual graph. And in the same direction, I would not add any edge because the residual is 0. Correct? So again in the residual graph, so this is again residual 2. So again, same direction, it would be 0, no edges. Right? No edges because same direction is 0, so 8. Again, 12, which is same direction is 0, so 12. In the opposite direction. What is this? 10, same direction.
So this residual 2 we are making from original graph, correct?
Every time we make a residual graph, we choose a path, we change the flow in the original graph by seeing whether it is in the same direction edge or at opposite direction edge. If it is opposite, we would subtract the same amount, right? The thing we added, we would subtract. So now we got a new graph. Now we got a new flow in the original graph from the first residual graph. Now with respect to this new original graph, we would construct again the second residual graph and again try to find the path in the second residual graph. Again, we would repeat the same step.
But the new flow, why are we taking along SABT?
SABT, yeah, okay.
Then why are we no? Because in the first residual graph, we took another path of SADBT.
No, we are not taking along SABT. We only took along SABDT. What did I do? I added 8 plus 4 here. I added 9 here. This is not along SABT, right? Why did I added 9 over here then? Getting the point?
Sir, in residual 2, should we add the AD edge, backward edge from D to A?
D to A.
D to A.
Yeah. But what would be the, so let me finish the edge. I mean, I would draw that. But the thing is, forward it would be 0 because I'm not sending, there is no residual capacity, right? So only a backward edge would be 0. So this is directed in this direction, right? Now I am sending a flow of 9 in the same direction. So what is the residual capacity? Residual capacity is 0. If residual capacity is 0, my edge would be like this. This is my residual, I mean, but it's meaningless to draw that. So let's not draw this. So only thing is I have a back edge of the flow that I have sent, which is 9. Now let us draw over here this particular, okay, so this I have not drawn anything. Sorry, this I have not considered anything. So it would be in the same direction, 4. Fine. Only the path where you have added flow, sorry, only the edges where you have added flow, you would consider them accordingly in the residual graph. Also here I have not added any flow, so let it be in the same direction, 7. And here also I have not added flow, 8. Here also I have not added flow, 16.
It's 4, sir, I guess. D to T.
Sorry?
D to T, 7 or 4?
D to T, 7, right?
4.
Or is it 4 or 7? What did I? 4, sorry. 4. Yeah. Fine. So there are a few intricate things that you have to keep in mind. So first important point is while making the residual graph, whatever flow is currently in the direction in the original graph, you would add a oppositely directed edge in the residual graph. So here the flow is 12, add an oppositely directed edge. And whatever is the residual capacity corresponding to that edge. So in this case, it's 12 minus 12, which is 0. So corresponding to that, you would add a edge in the same direction. So this is directed in this direction. So I would add a edge 0 over here. But since this is 0, it doesn't make any sense. That's why I'm not drawing. If it is non-zero, then I would have drawn. Like here I had drawn 4, right? So here we had this 4 because 12 minus 8 was 4. Anyway, so this is my residual graph. So that was one point. Another point is those edges where you have not made any change. So as Mr. Vimlesh was saying, that why are we considering the path SABT? SABT was considered in the first iteration. On the basis of that, I made this residual graph. In this residual graph, I chose the path SADBT. When I chose the path SADBT, I would not consider anything corresponding to SABT. I would only consider the edges in the original graph, which is along the lines of SADBT. And I would add or subtract the flow according to the direction in the residual graph. Okay.
Okay.
Fine. So now once I have completed the original graph's flow, I am again drawing residual graph 2, and this is my residual graph. Again, you try to find a path towards the end, right? I think I drew all the back edges, right? So this is 10, this is 9, 8, 12, 12. 4, 8, and 4, this I have not touched. Fine. Okay, so now again, tell me another path.
SCDT.
One thing, sir. So in the first residual graph, we took the minimum flow, and then we
sorry. I didn't take the minimum flow over here, no? Oh, sorry. I missed that. within explaining. Sorry, there is yeah, I missed that point, huh? Sorry, extremely sorry for that. Here it is. Minimum flow over here is 4, right? So it would be 12. Huh.
It will
So,
be like
correct,
12,
correct.
9. 9
So,
will be the minimum flow now.
Yeah, not 9, 4. Oh no. Yeah, 4. Here we have 4 now on the path. This is 4, right? This is 4, this is 4. In the residual graph, I have 4 as the minimum. Sorry. So let's revert back. I just forgot to discuss one point. So when we are picking the residual, the path in the residual graph, then again we will do the same step. I forgot that step completely. So the thing is, you pick the minimum, again the bottleneck capacity. So in the first path, we pick 4 as the flow because that was the bottleneck capacity. So again, we would pick the bottleneck capacity in the residual graph. So if I see in the path SADBT, my bottleneck capacity is what? Here it is 4, here it is 9, here it is 10, and here it is again 4. So 4 is the bottleneck capacity. Fine. So again, I would take 4, that is the minimum value, and then I would do the same process which I did earlier. So initially this was 8, so 8 plus 4 would remain 12, no problem. But here I added 9 mistakenly, it should be 4 because we are adding the maximum capacity which is 4. Okay, here also it would be 4. Here also, what was the value over here? 8, right? So 8 plus 4, it would be 12. So you pick the minimum value only. Yeah, everything else is okay. So now, but my residual graph would change because I have some certain capacity in the other direction. So let me draw the back edges now. So here it is only 12, no problem. Here it is only 12. But this would change because here what would happen is, so from, this is D, right? Yeah. So from D to A, opposite direction, I would pass the flow which I was passing. Sorry. And from A to D, I would pass the residual capacity, which is in the same direction. Same step. I just forgot to put the minimum value, which is what? 9 minus 4, 5.
5.
Here again, same direction, I would add how much? In the direction BB, B to B. B to B, I would add 6. So that is my front edge actually. Anyways, so B to B, I would add 6. And B to D, the opposite way, I would add the flow that I was passing.
4.
Fine. And this is 12, so that's fine. 12. So I got a new residual graph, and yeah, it's fine. Now you again pick a way to the from S to T. So I pick the way, let's say S C, let's say SCD, and let me take a back edge. So SCA, if I take SCA D T, SCA D T. Oh no, that is back edge.
From C, we can only go to D.
Yeah, that is fine. But what I'm trying to do is trying to take a back edge. So, okay, let's say D8. It might be a bad path to choose, but anyways, let's say D. Just for demonstration purpose, I'm choosing. So SCD, SCD. No.
Can we take S, C, D, B, A, again D, and then T? I mean, cycle will come.
You can do that, but it's unwisely. You are just increasing on the same path. You should always see one important point while taking path in the residual graph is choosing paths. You should consider the different edges, right? Because the more you can take any path, but the thing is you would continue your iteration for a long time. But if you take multiple different edges which has yet not been a part of the paths which you have chosen, so the algorithm would converge fast. Fine. So, but anyways, just to demonstrate the back edge, I'm taking the path SCA, then D. and then T. Fine, SCA DT. See, I am actually repeating the edges. Oh, SCA also I cannot do. Sorry, I did not see that.
Sir,
Not possible.
SCADT, is it not a package?
SCA I cannot go na. The edge is not there. See,
No,
A to C, yeah.
SCDBT.
SCDBT is a chosen path. No, it's not chosen, right? SCDBT.
B to B is a package, right?
Okay,
Is it
fine,
not-
fine. SCDBT is a good one. SCDBT.
No, now from B we cannot go to T.
Oh, yeah, B also we cannot go
Yeah.
to T.
Yeah,
That is why I said S, C, D, B, A, then D, then T.
That would actually increase your iteration a lot. See, actually, this is a good indication. This means that you have lesser path. Whenever you see that you have lesser path, you mean that you have very few iterations left to reach the solution. Right, but in my case, it is not a proper example because I wanted to take an example where you have this package and you would do the minus. But in exam, this is a good example because you would converge quickly because you are not able to find a lot of paths. But anyway, so let's proceed it anyway. So I choose the path which is available.
Final question.
Let us make the path BT in the original graph from 12 to 14. Then we will have.
I don't want to do anything about because again it would create confusion. So let me just state this thing. Only point that I want to show so as to discuss, I mean, so as to just keep this package thing, right? I was obsessed about it. Only thing that we have to be careful about that I was adding 8 plus 4, right? Why? Because here the flow was 4. Here the initial flow was 8. Initially we added 8, right? The bottleneck capacity was 8 and we added 8. And here we added the flow was 4 and this edge was in the path. This edge is corresponding to that edge. And it's in the same direction in the original graph. That's why I added 8 plus 4. If you pick a path in the residual graph whose edge is in the opposite direction. So let's say there is an edge. Let's say you consider this edge. And let's say this value was something 2. Suppose, right? In the path you consider this edge. Suppose. And here you see that original graph, the path is the edge is directed in the opposite direction. And the initial flow was 8. Fine. And in your path, this edge is there and its direction is this way. And this edge value is 2. So what would you do? You would do 8 minus 2, 6. Okay, so that is the only concept that I wanted to discuss. So whatever path you choose in the residual graph, if that path consider all the edges, if a particular edge's direction is opposite to the direction in which you have the original graph, then you subtract that amount. Do not add that amount. Okay, that's the only idea. Anyways.
What is the final question will be or the final answer? It is the path or?
No, the final answer is a flow that we will, once see.
So the options will be flow, is that so?
Option would be a flow. Yeah, you have to calculate the maximum flow.
Okay.
So see, let's in this example only where we were, this is not 2, this is 8. So I'm taking the path which is SCDT. SCDT, yeah, not D. Okay. So you take the path SCDT, you need to go up on SCDT is the path. Again, you pick the bottleneck capacity. What is the bottleneck capacity? 4. Right? 4 is the bottleneck capacity. So you add the bottleneck capacity. So this is my path. Okay, see the original graph and each edge on the same path. So I see on OSP, SP is 0, 16 and it's denoted in the same direction. So you add 0 plus bottleneck capacity, which is 4. Bottleneck of this, right? 4. So my flow is 4 over here, 4 over here, and 4 over here. Right? Done. So now I got another new original graph with a different flow. Again, draw residual graph. But now the thing is, if I draw residual graph, the problem is, see, will I get any possible edges, direct edge from 2T, I mean, which is direct residual edge, I mean. So what I mean is, so when I have these two edges, right, from T, which is going towards T, in the residual graph corresponding to this graph, right? This graph, after adding this 4 flow, this graph which I got, when I draw the residual graph, what would be the value of these two edges which are going to T? So just in residual graph, what we do, whatever is the flow, right? Here 12 is the flow. So you
It
add,
will become 0.
yeah, you add 12 opposite direction, and you capacity minus the flow 12, whatever that value is, in this case 0. So you would add in this direction, in the same direction, you would add another edge that is equal to the residual capacity. In this case, it is 0. Right? So that's what I'm asking. So the edge which would go inside T in the residual graph corresponding to this graph, both of this would be 0. And the opposite edge would be, this would be the flow 12, this would be the flow, whatever, 4. Correct?
Yes.
Right? So, I mean, so when you get that thing, now again you have to iterate whether we are able to find any other path or not. Now I'm leaving it to you whether you will be able to find any other path in that residual capacity or not. But yeah, so you would have to find whether there is a path, take the bottleneck, add or subtract in the original graph, then again create residual graph unless and until you are not able to find it. Finally, when you are actually getting an answer, whatever you, I mean, when you are not able to find any path, whatever answer you get, that is your maximum flow. But I would suggest, I mean, not suggest only, yeah, I would, as of now, I would suggest the whichever question regarding max flow comes in your examination, at first try to solve it directly, because if you, it might be a very easy problem. So this is the general idea. This is the, given a big graph, how can you solve it? So you take this way. But if it is a small graph, then maybe just by looking at it, you would be able to figure out the answer faster than by applying this whole algorithm. Fine. So from exam perspective, I'm saying just apply the basic, I mean, basic brute force approach once. If you see that it's getting very difficult, then I would suggest you to complete all other questions which are there. Then you should go for solving this by applying the residual graph algorithm. Otherwise, I hope that the question would be such that you would be able to do it directly. Fine.
So the question will be, we have to find the path where the
no, there is no path actually. See, it's not a shortest path we are considering here. It's the flow which can flow through that, I mean,
S to T, where you can send a maximum capacity of water or oil, right?
No. So, I mean, so let's say this is the network, right? Let's say let's say there is a network.
Small, just 4 vertices and just tell what will be the answer.
Right? Yeah. No, not answer. You would just find by, I mean, so if you see the lecture, I think in the lecture one example sir has given small, I mean this one. In the lecture one example is already there. So right. So like this. So you can just refer that to get the, I mean, if you want to just see a specific answer. The answer is just a flow, the maximum flow which can enter into the destination, right? Enter into the destination. That's the maximum flow which is possible. If you repeat this process and add the flow now, so whatever value you would get here, let's say you get 80 by 12 and here you get suppose 2 by 5, something like that, suppose. And you are not able to find any further residual, you are not able to, so this is the graph that you got. You created a residual graph after this. And in the residual graph, you are not able to find even a single path after this, right? In that case, since you are not able to find any single path in the residual graph, then you can guarantee that, okay, so since I'm not able to find, that means the algorithm is converged and 8 plus 2 is the maximum flow.
Okay, yeah, that's what's my question. Okay.
Okay, so that's the idea. And if you want a specific example, sir has taken an example, a small example, and he has shown the, I mean, the flow, what should be the flow. I'm not solving that because, I mean, you can just do that. The process I discussed, but again, just as a tip, I would tell you to not directly go into the residual graph way. Go for the normal way just by applying brute force and check what is the maximum flow that is entering into your your destination node. If it is getting very difficult, then you might apply residual graph way, but after solving all other questions.
Sir, can we find this easily by minimum cut process, or is it also going to be hard?
Minimum cut process, how will you do? You will have multiple subsets of different vertices in which one set will have S, another set will have T, and you would find what is the what is the flow or summation of edges going out of the first set, right? And that is your basically the difference between the flow. So the flow of this set 1, flow of set 2. Sorry. So that would be your minimum, your cut. So in order to find the minimum cut, again, you have to have multiple possible subsets, right? So, so you have set 1, you have set 2. Set 1 has the S vertex, set 2 has the T vertex. That's the definition of a minimum, plus some edges, some vertices, and here also plus some vertices. That's your 2 sets. Okay. Now, how to calculate the cut, right? So this is basically cut. So this is a cut, S1 and S2. The idea is S should be in one, T should be in another, and then you have some vertices. So as to isolate it. What do I mean by isolate it, and why do we call it cut? So you have to pick these vertices, or let me say you have to pick the edges in such a manner so that the vertices that come inside the set A and set B. So let's say this is my S, this is my T. Okay, I pick, so if I, which are the edges if I cancel out? So let's say it's A, B, and C. Which are the edges if I cut them? I cannot reach from S to T. Can you tell me?
AT and CB.
AT
and CB.
CB. Fine. So these are nearest to S, which if I cancel out, then I will not be able to reach T. Assuming these are the directions. Fine. So what I do is I do a set, let's say keep S and keep A in one set. Fine. And let's also keep C in one set. And let's keep B, T in one set. Fine. I'm kind of doing this. And then you calculate the flow which is coming out of SSC and BT, and you find whether, and the difference between them. I hope that has been discussed. So you find the net flow going out of SSC into BT. Okay. So you find that. So how can you do that? Flow coming out of S plus flow coming out of A plus flow coming out of C. Okay. Minus flow coming, so any flow which is not, none of the flow would go into S. All of the flow would come out of S, right? So minus component of S would be nothing. But from A you would subtract if there is some incoming edges into it. So you subtract that, and from C also you would subtract. Right? Normally, the way you find the flow between two sets. So you would find the two flows, and then you would see whether it is minimum or not. Again, you would take, okay, let's take S and A as one set, and let's take CBT as another set. Again, you would find the flow between these two, and see whether
both problems are complex.
So either way, there would be multiple possibility of subsets, and it would take you a lot of time.
So Tukka is the best option.
So that's why I'm saying that it's difficult, and what you should do is at first try to directly apply your basic brute force method. And I'm only stating this only because from your exam perspective. But obviously, you should understand the algorithm for your own knowledge purpose, because when you would code it up for larger graphs, then obviously your brute force would never work. It would take exponential time.
Yes.
Fine.
Yes.
So anyway, so very difficult question would not come from this particular topic.
Okay, so if the minimum cut problem comes, then I will find the maximum flow in brute force way, and that will be the answer for minimum cut as well.
If the minimum cut problem comes, then it would ask you for a, it would be given in the options, right? Because cut cannot be given in the form of a NAT. Getting the point. Flow is a number, cut is a set. It's a set, pair of set. So it would be in the form of option. So one best way is, if minimum cut comes, just pick the option and find the flow. The minimum one is your answer.
Okay.
Right? And if there is an option which says none of them, then you are screwed basically, because you cannot apply that. So anyways, but yeah, that's the idea. Fine. So flow, LPP, and last this week is discussed. Now, which week should I go first? Should I go to the dynamic programming part, or should I go to the string matching part? Which you feel is more
Dynamic program, please.
Yes, the
So
matrix
that part
part.
where there will be the questions will be asked.
That's a good demand. Okay, so I would go to the dynamic programming part.
Okay. From that portions, I think the question will come, right?
I did not give answer to that. I gave answer to more of you said dynamic programming.
Okay, thank you.
Okay. In fact, this is the bipartite matching. So where we apply full cursor as a reduction. So we learned about full cursor. We learned about reduction. How we do reduction doesn't matter. Not in the context of this course, but you can apply full cursor for do bipartite. That's one idea, and it might come as a statement or something like that.
So, sir, in bipart matching, we can see if more than two colors are coming while we are coloring the vertex, then it is not bipartite, right?
That is not bipartite or bipartite case, but matching is something different. Matching means you have to, I mean, let's say complete matching, then you have to match all the left side vertices with all the right side vertices depending upon the initial edges which were given.
Okay.
But whatever you are saying, that's correct. That's for bipartite, whether if a graph is bipartite or not. But
Yes.
if that question is asked, then no. The simple, so since this is also in the syllabus, and we had one graded question on that bipartite graphs would always have, there was a specific
even cycle.
Yeah, correct. So bipartite graphs can never have odd length.
Yeah.
Anyways, so where is dynamic? Okay. Okay, so dynamic programming, first of all, what kind of question might, so I'm not discussing very detailed, right? Because those things are there in the session. What I'm more concentrating on, what kind of questions you might face. Okay, so I would, after this, I would just go into all the dynamic programming algorithms, and then we would discuss each of the substructure and how to solve the matrices.
Yes,
okay.
Sir.
Yeah. So first of all, first important thing about dynamic programming that might come in the form of statement or somehow, that what are the two important properties which must be there in a problem so as to apply dynamic programming on it? Can someone tell?
We can even divide it into sub problems.
Okay.
Memoization.
Memoization is a technique to solve this kind of problem. It's not the property. What I'm asking is, you cannot apply dynamic programming or so to say memoization on any problem which does not exhibit these two properties. What are these two properties?
We can divide the problem such that subsequent iterations from of the previous steps are converging toward the solution of the problem.
Okay. So,
Sir, there should be always a smaller problem for a larger, like there should be a subset.
correct. And the idea is, if you can solve the smaller problem, then that should equally contribute to solve the larger problem. So that means, if I have a technique to solve a smaller subproblem of the larger problem, then that same technique, if I continue doing that on all the sub problems, right? Then the same technique should be able to fetch me the optimized efficient result even for the larger problem as well. Okay, so that is the idea. Now it might seem very trivial. I am solving small problem and all the small problem constitute the larger problem. So anyways, it should give me the correct answer. No. Let me give you an example. So we all have learned about the directed acyclic graph, right? Where we use the longest path, how to find the longest path. And we use the topological ordering to find the longest path, correct? Now, if I give you a graph, okay, some dot, there are many edges in the and vertices, and there again you have some vertices. Fine. And in between we have multiple, suppose vertices are there. Okay, and also edges are also there. I'm not drawing that, but I say you now what I do is, let's say I divide this part as one subpart, this part as one subpart. Let's say here inside this I have two subparts with the vertices. This part is one subpart and this part is another. And I tell you that you find inside each of this subpart, obviously you would have vertices and edges, right? Inside each of this subpart and multiple connections. So I tell you to find the maximum distance or and I tell you that all of these are dabs. Fine. And you have to find the maximum length path in each of these subparts. And you do that. Maximum length path in each of these subparts, right? So will that actually contribute when I join all of this together? Can I say that if the maximum path length here is 2, here it is 3, here it is 4, here it is 2, here it is 1, and here it is 3. If I sum it up, whatever is the summation, that is the overall maximum path length for the whole graph. Can I say that? No, that's wrong. You would not be able to divide the longest path problem into sub-problem and solve it separately so as to contribute to your solution. But shortest path problem, I mean the Dijkstra algorithm, right? I mean not Dijkstra algorithm, the problem, the shortest path problem. So shortest path problem with a little bit of tweaking, you can actually divide it into subparts and solve it. But that requires a tweaking. It's not simple. Okay. But anyways, so this was just an example that you cannot apply dividing into small problem and solving the sub problem to also solve the larger problem. That is not applicable on all kinds of problems. So the answer is, now this is the exact term and you should know about it because this would come directly in the exam, might come directly in the exam. Okay. sorry. So this property is called optimal substructure. Please keep this thing in mind, substructure. And the second property is overlapping subproblem for dynamic programming. Solving the smaller problem to contribute to the larger problem solution is optimal substructure. Overlapping subproblem means when you are solving a larger problem, these subproblems which you are trying to solve in order to solve the big problem, these subproblems are repeated. Okay, so when you are solving this big problem, then it might happen, not might, it would happen multiple times that in the process of solving it, you are solving one particular one or more than one small problem multiple times. It might not happen sequentially, but it might happen, it would happen. So what that means is, if I'm solving a same problem or sub problem multiple times, I can simply store the result when I'm solving it for the first time. And whenever next again I have to solve that problem, I can simply take that result without doing the whole computation. That is the whole idea of dynamic programming. So the matrices that you saw in the lecture, right? All the matrices, like we had this thing and we were in filling this matrices up depending upon some recursive some formulation, right? So what was this matrix all about? This matrix was storing the pre-computed data, and whenever again you actually need the same data, so I need P of ij multiple times. So this particular cell, suppose P of ij, I need multiple times. I'm just storing the data. Whenever again I need P of ij, I would access it from there. So this is called overlapping subproblem. So the subproblems are repeated multiple times. That's why you are storing it when you are first solving it. Later, when it is referenced, you are just picking the value from the position where you have stored it. And that's why you see in all the dynamic programming problems, there are arrays and 2D arrays or matrices where you store the value. Okay. So these two are the important properties which should be there in a problem in order to apply dynamic programming, and it's very important as statement wise. Understand this, it might come. Okay. So the next thing is, as someone said, memoization. So we would discuss that. That is again important thing. What is memoization and what is dynamic programming? It's very simple. So let's say in order to solve Fibonacci, right? Let's take the example of Fibonacci only. So I say Fibonacci of 10. In order to solve Fibonacci of 10, what are the values that I need? I need Fibonacci of 9, I need Fibonacci of 8. Correct? Two things, right? We sum it up. Then Fibonacci 9, I need what? Fibonacci of 8, Fibonacci of 7. See, subproblem is repeated. So this is your overlapping subproblem. Okay. Anyways, so let's proceed. Fibonacci of 7, Fibonacci of 6, and here I get Fibonacci of 6, Fibonacci of 5, dot dot. I'm not drawing the other side of the tree. You see that there are multiple overlaps. Fine. So the thing is, if we have this structure, there can be two possibilities of solving this problem. The first is, I got Fibonacci of 10. Now think in terms of programming. When you are coding it up, you have to code this up. What you can do, you can have Fibonacci of 10. You can start it from Fibonacci 10. And whenever Fibonacci of 10 is requiring Fibonacci of 9 and Fibonacci of 8, you call Fibonacci of 9 and Fibonacci of 8 recursively. In fact, that is what we have done in the general code of Fibonacci. We write f of n. Here we give the base condition, if n the base condition, and then we say else return fib of n minus 1 plus fib of n minus 2. Correct? So this is recursion. So when I require 10, when I require 9 and 8 to calculate 10, I simply call the function. Okay. What is the second approach that I might have? I know that in order to calculate Fibonacci of 10, I have to go to the ground level and I must have Fibonacci of 1, I must have Fibonacci of 0, right? And I must have Fibonacci of 2, because essentially we are doing n minus 2. So n minus 2, if I put n equal to 2, then only I would get 0. Right? If I simply put f of 0, and that is what I have, right? So n minus 2, in case of 0, what it would be? It would be minus 2. Now minus 2 is a wrong value, right? It's an illegal value in this example. So in order to decide what is the, up to what value I should have the base case, right? It's better to observe what is the term after subtraction in any of the program that you do. In Fibonacci, it is n minus 2, so it's better to calculate the base case up to f of 2. Okay, do not put it in the recursion, just calculate it manually, the base case of induction, how it happens. Okay, anyways. So the second approach is, so I know I would need f0, f1, f2, so I calculate that. And I keep it pre-calculated, right? Then I would proceed from bottom to top. I know f102, I would use that. So I would use f of 1 plus f of 2 to what? If I sum it up, it would be f of 3. Correct? So I calculate f of 3 by using f of 1, f of 2, because I have the f of 1 and 2 earlier. So this is what? Bottom up approach. Second one, that you had the initial values calculated at the bottom, and then you are going to the top up to f of 10. Okay. And this is the top-down approach. This is bottom-up approach. So this is actually called dynamic programming, when you are actually using the base values pre-calculated, and on the base values you are actually trying to calculate the upper values. And that's why in most of the algorithms that we discuss, we have those matrices. Again, I'm coming back to that. And you would see that in the base case, we would actually initialize 0 or 1 or whatever. And depending upon these in the matrix at the end, we would initialize 0 or 1, whatever it is. So we would come to that, right? And on the basis of these values, I calculate this cell, I calculate this cell. And again, on the basis of this cell, I calculate this cell. Accordingly, we proceed. So I store the base values first. So this is dynamic programming, bottom-up approach. If I come top-down in a recursive way, that I am not storing or doing, I'm not doing initial storage of the data. I am coming from top to bottom, and just I would call recursive. So this is called memoization. Just two different terms. This is called memoization. This is called dynamic programming. So top-down is memoization, bottom-up is dynamic programming. But we would focus mainly on dynamic programming. Sorry. So this was about the conceptual part. Whatever theory would come from these definitions: optimal substructure, overlapping subproblem, memoization, dynamic programming. What is the difference between these two?
So is it like dynamic programming is a part of memoization?
Part, can you say that? I mean, one is coming top down, another is coming bottom up. You can say that both of them are same, or let's say sibling approach to solve similar kind of problem. That should be a better statement to say, right? But they are not subset superset relation, because one is not computing the initial value. So memoization is not computing your base values, right? It's just whenever you require something, you call recursive. But what dynamic programming is doing, it's initially going to the base level, ground level. It calculates what are the ground level values depending upon the boundary condition, right? And then on the top of that, it builds the next values by following the recursive structure. Recursive structure means those equations that we saw, like in matrix, it is something like in longest common subsequence, it is LCS of I minus 1, whatever. So that's the idea. So they are both similar approach to solve similar kind of problem, but one is not part of either, so to say.
So memoization avoids overlapping or not?
No. Obviously, see, one important thing that I raised. So you can actually store this value in memoization as well, right? The thing is, I am not calculating the base case, right? But when I actually, I draw this recursive tree. So basically, memoization directly depicts this recursive tree. F10 is called, F9 would be called, then F8 would be called. But what I mean is, let's say, for a shorter example, what I mean is F3, F2, everyone would use the overlapping subproblem. Otherwise, it is of no meaning. F1 is the base case, right? Fine. Did you have any repeat? Yeah. So I have a repeater. So this is memoization. Okay, I'm not calculating F1 initially, or F0 or F2, so to say initially. I'm calling F3, then recursively F2 is called, F1 is called. Now you see, I hope you all know how the recursion tree works. So which one is the first function that would actually be executed, that would actually be completing its execution? Can you tell which particular function?
Leftmost F1.
Exactly. So this F1 is the first function which would complete its execution, and then it would return back to it. And actually F2, this F0 would then return back, but anyway, we are not discussing that. But F1 is the first function that would complete its execution. Correct? When this F1 has completed, this F1 has yet not been executed. Correct? So whenever I am computing this F1,
what about F0?
F0 would be computed in parallel. No? So basically, I would do n-1 plus n-2 in the recursion. Correct? So at first, this would come in. So these two would be parallelly scheduled. But the thing is, since it is first, it would be calculated first. After that, fn minus 2. So f0 would be calculated just after f1. And then both of these value return back to f2, and then f2 would be calculated. And then f1 would be calculated. And then again f2 returns and f1 returns, and then finally f3 is calculated. So siblings are calculated.
Basically, this is base case condition which will calculate first.
Exact. In dynamic programming, yeah. In memorization also, we do not pre-calculate it, but at the end of the day, you would actually do that first.
Yeah, when we go to the last recursive call,
yeah,
and which it will take it to the base condition,
yeah,
then it will be calculated,
exactly,
and then it will be traveled backwards.
Exactly.
But how can we say whether f1 will be calculated first or f0 will be calculated first?
No. So when you are right, so this is a programming concept, not algorithmic concept. When you are writing return fn minus 1 plus fn minus 2. So which term is first? Which particular call would happen? So we are in DB. So I'm going back to DBMS a little bit. So we discussed about the call stack, right? I don't know in CT where you have learned about call stack. So when your function is called, it would be represented in the form of a it's called an activation record, but basically you mean that whenever a function is called, representation of that function is stored in the form of a stack. Not very important if you don't get it. It's not important. I'm just answering this. But in DBMS, we have discussed it, what is call stack, right? So I'm answering from that point of view that whenever you are writing this statement, so which function would go into the call stack first? I mean, which one would be at the top? That would be executed first. Fn minus 1 would be at the top of the stack because it's actually first. So it would go first. And then fn minus 2 would be. Okay, because if I just reverse it, fn minus 2 first and plus fn minus 1, then obviously f minus 2 would be the left one and it would be calculated first. Okay, so this tree representation is a representation of how the call stack is structured. And yeah, nothing else. So leftmost element is always the element which would be calculated first, because that's the first call stack. That would be popped, then this would be popped, then both of these result would be coming into here and it would be popped. But anyways, we are not going into that anymore. Let's discuss the algorithmic thing. So what I was saying is, let's come back to that question whether memorization uses the overlapping or not. Yes, it uses. And why it uses is, so this one would be calculated first, correct? Once this f1 is calculated, you store it in an array. Now you store it in an array. You did not calculate f1 initially on the basis of boundary condition. Rather, you actually recursively went down to the base cases and then you calculated that. Okay, it's the same way of saying different way of saying the same thing in two different ways. Okay.
But is it the same case of dynamic also, right? We went down and then calculated base case. Instead of recursion, we stored the value. That's the only difference.
Yeah. In dynamic, we calculated the base case first. We never. So let me go to the examples again. You would see what did we do. So in edit this, let's say in subsequence, what did we do? Initially, these terms were 0. Remember, whenever it is m. So what was that? That is a base case.
Okay. Instead of recursively going, we directly started from the base case. That's
by using the base condition. Yeah.
Okay.
Boundary condition. Sorry, boundary condition. Boundary condition means what? I would come to all those things. It's just after this. That when your I is equal to m is the length of your first string, and your j is n is the length of your second string. I is the iterator over first string. J is the iterator over the second string. And you are trying to find a subsequence or substring or subword or whatever on two given strings of length m and n. So when I see that, let's say longest common subsequence of I comma j gives me the longest common gives me the length of the longest common subsequence between string 1's I position and string 2's j position. String 2's j position. If this is the meaning of LC of ij, right? So what was our condition? When I is equal to m or j is equal to n, that means either of the string has reached or both of the string has reached its end. So when you have reached its end, there is nothing to compare. So at that time, the longest common sequence does not exist because you are comparing a blank field. The string has already been ended, right? So that's why what would be the value of LCS? It would be 0. This is the base condition. This, whatever I talked just now, that when you have reached the end, then LCS of ij is 0. So this is the boundary condition or base condition, and that's why I view it like this, because the first string is like this. So this is the end of the first string. Second string is like this. So this is the end of the second string. So this means here it is m, here it is n. And that's why these two rows and columns are same. I would come to that when we discuss LCS. Okay. But that's the idea. You have the boundary condition, you compute the base case on the basis of boundary condition, and then you build up upon that in dynamic programming. In memoization, you actually calculate the base cases, but the thing is you do not calculate that at first. You simply call the function, recursively you went down the ladder up to the base case, calculated the base case, and then you can use this in an array, and whenever this F1 would be called, it can directly retrieve this data. It might not have to compute it. So memoization is also using a memory, right, to store the data. You can use that. Okay, but the thing is, only difference is in the way we are approaching to solve it. In memoization, we are coming from top to bottom. In dynamic, we are at first calculating the bottom cases and then build up upon that to the top cases. So that's why DP is a bottom to top method. Memoization is a top to bottom method. They are exactly the same thing to do the to solve similar problems. Okay, enough of discussion on that. I mean, it should be okay with it. Now let's come to the more important parts.
Hello, sir.
Yeah.
Sorry for interrupt, sir. Is there any questions will be asked in the topological sorting or BFS DFS tree in terming?
Should I tell you about it? I should not
I'm
even
sorry
tell you.
for that, but actually.
No, I can't tell you. Obviously, it's an important topic, so you should expect questions.
Okay, thank you so much.
Yeah. Anyway, so let's come to this now very fast. Like, I would just briefly discuss this grid because it's not that much important. Where is that recursive definition? So anyway, so let's so let's say over here I am. Okay, so consider this particular vertex. I am over here. Grid path means I am assuming that these problems you all are familiar with. I am just repeating it, the main concepts. So you are at this vertex and you have to reach over here, right? Not at this vertex. Suppose you have to reach over here. And how many paths from 0 to this particular vertex? So let's say this vertex is ij. So I say P of I comma j. How many, what does this P of I comma j give you? P of I comma j is the 2D matrix. This 2D matrix is P of P, right? Okay. And my question is, what does P of I comma j store? P of I comma j stores the number of paths from 0, 0 to I comma j. Okay, so this is what P of ij gives you, and obviously, if your question states that what are the maximum number of paths to reach 5, 10, then you can use it in a form of a dynamic programming and solve it. So for P of I comma j, a random vertex over here, what is the recursive solution? I mean, recursive structure on which we will build upon. So I know that in order to reach here, I can go either towards right or I can go towards top. I cannot go down or I cannot go left. So if I cannot go left, I cannot come from this side. So that's not a possibility. If I cannot go down, I cannot come from this vertex. So that's also not a possibility. So the only possibility is to reach this particular vertex is I can come from here or I can come from here. Two possibilities. What is the coordinate of this particular vertex? If it is ij, right? Now this thing is a little bit. Your voice is cracking. Your voice is cracking. We cannot hear it. Okay. no problem. Okay. So the thing is, you have to be a bit careful about it. In the examination, whenever you get a dynamic programming problem, okay, try to actually see the problem. And if a matrix is given and let's say the recursive substructure is asked from the option, choose the correct recursive definition. Try to observe the matrix properly. If it's just, let's say you know the LCS, longest common subsequence. Okay, you simply take the, you know, the longest common subsequence recurrence and you simply pick the correct option. It might not be correct. Why I'm saying it might not be correct? Because let's say in this example, I can consider I plus 1 j or I minus 1 j, depending upon from which side I am considering the origin. Here I am considering the origin from here. So obviously this vertex is at a lesser value than this vertex. So obviously this vertex coordinate would be 1 less x-axis. So I minus 1 and j is same. And this vertex coordinate would be 1 less y-axis, but I is same. So I comma j minus 1. Okay, if I consider 0 from here, then the whole thing would change. So please bear attention in the examination. Observe where is the origin given, or if it is some other problem, observe from where the base case is starting. Accordingly, you should take the correct recursive definition. Question might come like a matrix is given, right? For a particular problem, problem definition is also given. The values inside the matrix are also given. You have to choose from the option the correct recursive definition. Okay, so observe from which direction the matrix is growing. Just don't mug up the recursion and write and tick the correct option. Tick the option. The origin might be changed in the question. Okay, so here it will be I minus 1 j and I j minus 1. And like this, what we see is, if this is the general case, right? Okay, so I did not write it. So P of I comma j, recursive definition would be P of I minus 1 comma j. That is the number of paths to reach P of I minus 1 comma j plus the number of paths to reach I comma j minus 1. Right? Using these two possible paths, I can actually reach these two vertices. Summation of possible paths, I can reach this vertex. So this is your recursive definition. And regarding your base condition, right? Now, if you see, when I will get the base condition, I am doing here minus, and here again I am doing minus. So I am subtracting both the coordinates. So obviously my base condition would be towards the bottom because I'm subtracting. So every iteration I would go on subtracting I minus 1, minus 1, minus 1 till I reach 0. Correct. So my base case would be, what are the possible two base cases? Can someone tell me? If P of, I'm doing minus 1 in this coordinate and keeping this constant. So obviously one time I would reach 0 in I, but I would have j as same. And again I would, one time I would reach, I would be same, but j would be 0 corresponding to this one. Because this can be implemented in the form of a recurrence, right? You would do minus, 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 minus. So in order to reach this vertex, you are considering these two. In order to reach this vertex, which vertex I would consider? This one and this one. Right? In order to reach this vertex, I would consider this one and this one. In order to reach this one, I would consider, so there is a recursion going on, correct? So if I see that these particular set, and when I, at the end of the day, when I reach these particular vertices, these are my base case. Either I is 0 or j is 0. Correct? So if I say you, now let's erase all this. Now this is the question. If I say you, how many, what would be the base case? Because we know in dynamic programming, we have to store the base case in the array first. Okay. And then upon that, we would apply this. And then upon that, we would apply this formula and simply apply this formula and grow upon that. You would get the answer. Correct. So, but before that, I need to have these values, these base cases. So what would be the first base case is this one, second base case is this one. And if you see that, let's say any vertex I take on corresponding to this base case. So OJ, sorry, 0j. 0j means x is 0 and j is some value. So let's say this one. How many paths are possible from 0, 0 to this particular vertex?
One path.
Only one path, correct? Because you cannot go left side. So the option of going towards right and then going up and then coming towards left, right? This is not allowed. So if coming towards left is not allowed as a part of the problem definition, and I have a vertex on this line, then I can never go towards right. I always must keep on the same line because I am not able to come left. So if I once go right, I cannot come back on this line. Correct? So that's why whatever vertex on this line I have, the only possible path from 0, 0 is the straight line. You can go this way. I mean, to each of the vertex. So only one path is there. Fine. So the idea is this thing that you have only one path, and that's why the base case is 1. Accordingly, here also the base case is 1. Due to similar logic, you cannot come down, so you cannot go up. So you should be on the same line. Okay, so you have the base cases. Now, if I just simply delete all that, you all know the base cases. So that's why you see the matrix over here. Right? So base case is 1, 1, 1, 1. So here also 1, here also 1. All this would be 1. So all these values, in order to reach, I have only one path. Now what would be this particular value? It is 2, you can see that, but how it is coming? We discussed that this is what? Summation of this one and this one. P of I minus 1 comma j and P of, which is this one, and P of I j minus 1, which is this one. Right? I do a summation, I got 2. And same thing, 2 plus 1, 3. 3 plus 1, 4. 4 plus 1, 5. 5 plus 1, 6. Right? Accordingly, what would be the value of this particular vertex if I say? Right? It would be the value of 4 plus whatever is the value over here. Whatever is the value means, here I have 3, right? So 3 plus 3, 6. Correct? So 6 plus 4, 10. Accordingly, you go. So once you find the base case, and so 2 work you have to do: find the base case, and second work is find the recurrence. Once you do that, simply fill the matrix by applying it. That's it. Okay, so that's the grid path. The recurrence of grid path is P of I minus 1 comma j plus P of j comma I minus, sorry, I comma j minus 1. That's it, and the base cases are 1, 1. Accordingly, you fill the matrix we discussed, and if you get a block, then obviously that should be 0. So that is another case. So the third base case, right? I did not discuss that. So if sorry, if your matrix, right, matrix of I comma j, if that is a x, right? Let's say you denote the block using x. So if that is a x, then P of I comma j would be 0. Right? So this would be 0. This would be 0, and accordingly, if I want to calculate the value of this one, what would be my answer? This is again 0, right? This is 1, I know. This is also 1, I know. So what would be this value? 0 plus 1, 1, correct? And this is 0 plus 1, which is 1. So in fact, that's the idea. If you have to reach this particular vertex, the only path you have, because this is blocked, all this is blocked, only path you have is the one path, which is like this, and then come like this. That's why it's coming 1. Okay, so first grid path is completed. Now let's come to the next discussion, which is your subsequence. So again, this is nothing difficult once you figure out the recurrence.
One thing, sir.
Yeah.
I mean, it was mentioned in the slide, memoization never calculates for the shaded region.
For the?
But shaded region, but the dynamic programming blindly calculates everything.
Yeah. I mean, memoization you are calling on the basis of. So what I mean to say is, yeah, here memorization, you're coming top to bottom, correct? So when you're coming top to bottom, you would only go for those particular value which is required, right? Let me just give you an example. Let me give you an example. So let's say there is one problem where the recurrence is p of I minus 2, comma j. Okay, let's say one particular is in this form. Fine. And I always say that the maximum length of I, right? I mean, let's say there is a string and I is iterating on that string, and the length of that string is always even. This is a condition which is given. Length of the string is always even. That's the condition. And this is, let's say, my recurrence. I mean, let's say there is something else, some expression is there, I'm not worried about that. I'm just stating, let's say p of I minus 2 comma j is a part of that expression. Do not consider this with grid path or anything. I'm just telling a vague scenario. Okay, so there is a problem in which you have to traverse on a string. I and j is used to traverse on that string. String is always be of even length, that is given. Okay, so 2m, right? Some variable 2 into m, or let's say 2 square into m, or whatever. Now, if that is the scenario, would I ever need p of 3 comma j, p of 5 comma j? These values would I need?
No, I mean, that is not the condition.
Correct, right? But so if that is not the condition, but when you are actually coming up from the base case in an array is continuous. It would be 0, 1, 2, 3, 4, 5, 6, like that it would grow. So when you are coming from the base case of the array like this from the top, you would obviously encounter these cells corresponding to 3 comma j. You would obviously encountering these cells corresponding to 5 comma j. So in those cases, you have to apply the corresponding logic according to the question. If the question is saying these are invalid, right? Then you simply put the odd places as 0. Like here, whenever we got a block, we put 0. P of I comma j as 0. So according to the question,
Okay. So even though we are putting 0, but we are doing some work there in dynamic programming.
Yeah, you have to calculate that, because in dynamic programming, essentially you are running a 2D loop to iterate through a 2D array. Am I correct or not? What are you doing in all the programs? Simply you are running a 2 nested for loop to iterate.
Yes, we are visiting the all the array elements and
Correct,
putting
right?
the value according to condition.
And according to the recursive, this recurrence, whatever we discuss. So we are just simply writing a 2D loop. That's what I am doing. So if you are writing a 2D loop, it is not discontinuous. You would write I equal to 1 to n and j equal to 1 to n. So you would encounter values, this odd values also you would encounter, and that's why you have to put some value in them so that it does not affect the logic of your problem. So in dynamic programming, since you are coming from bottom to top and you are running on an array, you would encounter these cells. But memorization, what is happening? You are simply calling recursion. So if you do not have this p3j, would you ever have a recursive call of p3 comma j? You would never have, because if the length is even, so -2 would always give you an even number, right? So all the recursive call that you will do, that would be some even number, 2 comma j, 4 comma
But
j.
how about the base case in memorization then?
So obviously, yeah, correct. I am coming to that also. So when you are doing I minus 2 dot dot dot. So what would be the last value? It would be 2 and then 0. These two are also even, right? Yes. So in the base case of memorization, you would actually have these two as the base case. Doesn't matter, it's again even. You are solving the base case, but you did not go for the base case 1, because that's odd, but dynamic program would actually take the base case 1. You have to put 0 or some value over there depending upon, so that it does not affect your algorithm. But in dynamic programming, you would be coming to the base case of 1, but here you would not do. Here you would only go to 0, or let's say if the problem demands, you can also consider 2 as the base case and 0. Or if you only have one base case, it would go to 0 as the only base case. Right? So that's the logic behind memorization. You could only call the required parameters or make the required calls, but dynamic program will go through all of them. Fine. So let's come to the subsequence. Fine. So it would not take a lot of time. Subsequence, again, what we do is let's come to the direct. I'm not discussing what is subsequence. I hope you all know that. If you simply do matching, it would take order of mn square. I mean, so because you have an m length string, you have an n length string. Each of these position you have to match this n length string, and then again you have to compare that with itself, right? So from each starting position, scan could be order of n, and obviously you can have you're not matching the whole string, right? In KMP and all those algorithms, we are matching the whole string, but here we are not matching the whole string. We are only checking for substring. Right. So when we are checking for substring, in case of I have, let's say, A, B, C, D, A, B, I can have a substring among this. I can have a substring among this. Anywhere a substring can be possible. Right. So if my pattern is n, right? So I have to calculate m into n possible pairs. And in this m into n possible starting points, not pairs, sorry. M into n possible starting points. In this m into n possible starting points, I have to scan n. Scan this, right? For every mn starting point, for each one of them, I have to go through this whole second string to check whether a substring of the second string is matched over there or not. So m into n, which is 7 square. It's actually important. Keep this thing in mind. Might come as an MCQ. Let's quickly come to the recurrence. Yeah. So let's say this is one of my string, and let's say this is one of my string. Okay. So how can I do the subword checking? I would compare, let's say I is traversing on this one, J is traversing on this one. Okay. And what I'm doing is I'm comparing basically I and J. That's it. I compare. So this is okay. So here it is used A and B. I have taken the symbols as A and B. Let's say this string is capital A, and let's say this string is capital B. Okay. And here whatever small a you see, that is, let's say this is equal to my capital. Okay. So basically, I mean this small a is my capital A in my representation. Anyways, so I compare capital A of I, basically the first position of the string with the first position of this string. If there is a match, then what can I say? Right? What can I say about it? I can say that whatever, okay, so let me just process it from the other way. What I do is, according to this formulation, what I would do is I would start from the back. Okay, so that's what I was saying. In some, we can also start from starting. We can also start from back. So in our course, we have started from back. But in the question, it might come that you have started the execution from the first left-hand side. So how it would be given in the form of a question? The matrix that you would see. Okay, I would come to these topics, these expressions a little later. Let me just discuss what I mean. So if you see, the matrix is given over here, right? Over here, the matrix is given. So let's say if you see, the matrix is reverted in the question. Okay, so you see 0 over here. Likewise, it grows up to 6 or whatever. Okay, 6. And likewise here also, it grows in the opposite direction, 0 to 6. Then what would be the recurrence? Would it be +1? So what I mean is, so I'm assuming some things, that these basic things you know. It would not be +1, right? What would happen then in that case?
It will be reducing.
-1, exactly. It would be -I-1, J-1. So be very, very careful about it. Do not just simply take the options by seeing, do not observing the matrix. Okay, read the question statement, observe the matrix that is given. Then you choose the recurrence. Accordingly, it can come in another way. The question might come in another way. Question statement would be given, recurrence would be given. Now you might see that where we have used LCW of I plus 1, j plus 1. And in the question paper, the same question about longest common word is given, right? But the index, the recursive structure which is given, I mean this formulation, right? The formulations are given in a different way. You see I minus 1, j minus 1. So do not get confused over there. It's just the matrix is reverted and you have to start it from the diametrically opposite end. That's the idea. Fine.
Yes,
Okay. Great. So, but this idea would say if there is plus one in both, there minus one would be there in the both the case. Okay, great. So we compare from the right hand side. Okay, let's stick to what it is there in the lecture as of now. We compare from the right hand side. So I is there, j is there. So I compare B and A at first. If there is a match, there is not a match. If there is not a match, no question of, I mean, common word or anything. So I say it is 0. Fine. So again, I would proceed further. So I see whether A is a match with C or not. If A is a match, then it's okay. It's not a match. I would proceed further. Likewise, I would go. So that is governed by simply by this equation. These two equations. The base case is if there is not a match, you simply the longest common subword is 0. If there is a match, so let's say, is there even a match? Yeah, so this is a match. Okay. And also one important point is you can even have match like this, huh? Right? So I and J would be in a 2D loop again. When I'm doing dynamic programming, it would be I would be outside loop, J would be inside loop, correct? So for I, all the J's would be possible. That means when I get a mismatch for B and A, I would again check B and C. I would again check this B and C. Then this B and B, I get a match. Okay, so it would proceed in that manner, but I'm not discussing how it would proceed. That we would see in the matrix. But what I'm saying is, let's say I got a match over here. Consider this match, A and A. Fine. So what does this match mean? When I see a match in the middle of both of these strings, I have already iterated through this part, this part, and in this string I have already iterated through this part. So, but this is a match. When this is a match, I might also have had a match over here, right? I don't know. When I'm executing this, I don't know what was the previous state. Okay, so I might as well have a match, I mean, in the next comparison, right? So that's what we write over here is number of I plus 1 and J plus 1. Right? So we have calculated till over here, let's say there was a match and that match length was 2. Now I see that even the, so let's take this string to make it simpler. Let's take this string. Okay. Here C is there, here X is there. Here let's say P is here, here Q is here. So obviously P and Q is not a match. Okay. And then at some point of time I would come to B and B. So it's a match. Okay. That's done. So if it's a match, I would do I plus 1, J plus 1, both would be increased because there is a match, right? If there is a match, I'm coming to check what is the next common character in both of the strings. Okay. So I come over here in B and I come over here in B as well. So when now I am at this level, consider only at this level, this second B. So I see that this B and this B is also matching. So when I see that this B and this B is also matching, that essentially means I also might have some match earlier, which was true. I had a match of B and B over here as well, just before it, right? And I also have match currently in this B. So what does that mean? Since this is a match, I would add 1 plus, what is LCW? LCW is the length of the common match, right? Common word. So I have a match over here. That means I can add 1 character plus whatever was the maximum length of match I had just before my current character. My current is this one, plus whatever match I had till this part. Now I see till this part I have a match of 1 because P and Q was not matching, but B and B again matched. So 1 plus 1, this one is nothing but your right, because this is plus 1, this is increasing in this direction. So that's what the recurrence is saying. So 1 plus LCW of I plus 1, J plus 1. If there is a match, if there is not a match, no question of common. So we go for 0. And obviously, what are we doing over here? Plus. The best way to figure out the base case is you observe what I am doing in the recurrence. Am I doing subtraction or addition? I am doing addition. When I am doing addition, what would be the base case? The end of the string. If I am doing subtraction, what would be the base case? 0, right? Because I can go up to 0. So here, what is the base case? The end of the string. That's why you see M, N, N, and N. Okay. So this is what I was talking earlier, that when you have reached the end of the string, the common is 0, right? There is no, you have reached the end of both the string, there is nothing common. But when you have even reached the end of any one of the string, that also would be 0. The length of the common subword would be 0 in that case as well, because if one string you have reached the end, I mean at the 0, sorry, at the end, right? So there is nothing to compare in a null character with the other string. Other string is left over, but you do not have anything left to compare in one of the string. So again, the longest common subword would be 0 length. So these three are the base case. So either I plus 1, J plus 1 is happening. So I individual, so the second coordinate can individually grow up to the maximum length. That is one base case. First coordinate can grow up to individually up to the maximum length. That is one other base case. And both of these characters can grow up together up to their maximum limit. That is the third base case. All of them would be 0 because in either one of them you have no common character left to be compared. Fine. So these two are the recursive case. These three are the base case. You simply draw it. Obviously, the base case you can understand M and N, which is the last part. And since these are the base cases, that's why in the matrix we used to fill the base case from the last, right? Because 1, 0, 1, 2, dot, 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 this would be M, 0, 1, 2, dot, 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 this would be N. So these two are the rows and column which we filled up first with zeros. And then we applied this condition and this condition to simply calculate these cells. So let's go to the matrix and simply apply. See, that's why this direction is given in this way. Because obviously 0, 0 is something you have to fill at first, right? Like this, you have to fill all this 0. If I come to the bottom, you would see. Okay, so all of them are 0 over here and over here. And simply now you apply the same logic. So how can we do it? See, if the matrix is given to solve, how can you solve it? Right? So these values would not be given to you. So you have to calculate that. So let's quickly do that. What was our condition? The condition is if there is a match. If there is a match, then the condition was what? 1 plus LCW of
Max
I plus 1, J plus 1. If no match, what was the condition? 0. Okay. Is there a match with this two? There is a match, correct?
Yes.
So just draw a line from these two parts where it is, the row and column, the common part. So this is the cell, right? Corresponding to these two. So what should be the value in this cell? Let's have that. So I see there is a match. What if there is a match? This is the condition that I would apply. So 1 plus LCW of I plus 1, J plus 1. I and J means this cell now. What is I plus 1, J plus 1? This cell. So what is this? 0 plus 1. Answer is 1. Okay. What is, let's say, take any of them. So accordingly you fill it up. So is there a match over? Consider this particular line for C and for T. where I am intersecting, over here I am intersecting, correct? So let's see over here what's the character C, and over here is the character is T, right? So I'm comparing C with T and putting it over here. Is there a match or not? No, C and T are not matching. So put 0. Again, is there a match or not with E and T? Not matching, 0. Is there a match or not? S and T? No matching, 0. Accordingly, all of these are 0 because none of them are matching with T. Done. So we have these columns are done. These are done as the base case. This one column are solved now. Now let's see this one. P and E. E and T. This one not matching. C and E not matching. Now E and E. E, E. So I have a match over here, correct? Sorry, what this one? This one, right? So I have a match over here. So when I'm over here, what should be the value of it? 1 plus 1 is there, plus HWI plus 1, what is 0 again, right? So 1 plus 0 is 1. Accordingly, if you see over here, let's see this case, right? So if I see over here, what is this? S and S. So this is the matching point. Consider this particular index. So S is there, S is there. Yes, there is a match. Since there is a match, what I would do? This cell would be equal to 1 plus this cell, which is 2. Simple thing. Only important point from your exam perspective is two kind of question can come. Either the matrix would be given, you have to find the recurrence, or the recurrence would be given, you have to calculate the, I mean, let's say the recurrence is given, and let's say we say what would be the value of the index 2 comma, sorry, what would be this 0 1 comma 2. Okay, the question might come in this form. If this is the problem statement, if this is the recurrence, and if these are the base cases, then what should be the value of the cell 1 comma 2 in the matrix? Okay, so you have to apply accordingly and answer. So that is one possibility. Other possibility is the recurrence. Matrix would be given, you have to see, you have to choose the recurrence.
Okay, so, and the complexity here will be MN.
I mean, most of this dynamic programming complexities would be just the time taken to iterate through the array. Because you have the base case and you are applying a constant time recurrence, so it would be MN.
Okay.
In fact, that is there if you see over here somewhere. Yeah. Fine.
Yes.
Okay, so that was your longest subword. Now let's come to longest common subsequence. What is the difference between subword and subsequence? So if I have A, B, C, A, B, C, okay, and what would be a subword? A subword would be a subword or substring. Okay, both of these are same thing. Substring or subword would be a continuous sequence of characters in a given string. So CAA is a substring or subword. BCAAB is a substring or subword. But if I say BAC, is this a subword of the given string? No, because I do not have anywhere inside the string where I have BAC as a continuous sequence of character, right? But if I say BAC, yeah, so BAC is a subsequence. I can say that BAC is a valid subsequence of the given string. Now, so what is the definition of subsequence? Definition of subsequence is it can be discontinuous, but it should be in the same direction. That is, I'm picking up B. Okay, B. I'm picking up A. So just pick up any of the A which is after B. So let's say I can pick this one as well. I can pick this one as well. As long as I travel, since I picked B and I'm going in this direction, as long as I travel in this direction, I cannot come back. Okay, I cannot come back once I proceed further. So let's say if I pick this A, the second A, right? This A I pick up. And let's say here again I have another A as a requirement. Right? So then I cannot come back from this A to this A and say it's not a subsequence. I mean, from your algorithm perspective. So the idea is you should always pick the first occurrence of that character. Otherwise, it would not give you correct answer. Fine. So if I again restate the algorithm is you pick the first occurrence in the same direction of the given character. So I have B, I pick B, okay, fine. I have A, pick the first occurrence of A after B. It might be not consecutive. So here C is there, therefore it's not consecutive, but after that I have A. So fine. I pick up this A. After that I have again 1A. So okay, fine, I again have this 1A. This time it was also consecutive. And finally I have 1C, but here I have 1B. That doesn't matter because we are not searching for subword or substring, but I have a C after that. So this satisfies. Okay, so let me delete this. Yeah. So I have actually B, A, C. So difference between subsequence and subword is it might not be continuous. Okay, so that's the idea. Now the recurrence of the subsequence. How to apply the recurrence of longest common subsequence. So longest common subword, two recurrence are if AI not equal to Bj. AI, A and B are the two strings, right? A is of length M string, B is a length N string. So if there is a mismatch, I would allocate the sorry, what was the name? LCW, right? So I am writing now LCS, right? So if there is a mismatch, can I write LCS? Sorry, can I write 0? That's the question that I am asking.
No,
In case of
before whatever match we write that.
yeah, but if there is a match, would there be any difference?
Can add +1.
1 plus LCW of I plus 1 J plus 1 was the previous case.
So here we take max, I guess.
Are you sure about it? So don't think I guess, just logically. So if there is a match in this example that we took, if there is a match, what am I doing? So let's say I have the first match B and B. What did I do after that?
We'll add one and then search for.
Proceed further, correct? Exactly. Yes. Proceed further, and since you have a matching, so if I come to the recurrence over here, you see the recurrence. You add one, you proceed further. I plus 1 J plus 1 means what? You come to the next, in both the strings you come to the next one, right? So basically for matching there is no difference because this is the same condition as LCW, right? Same thing we did. If it is matching, I'm going for, but the difference is in the opposite case. So if I'm writing if AI not equal to B, so what I would in LCW I simply wrote 0 because I need a continuous string, right? If even there is a discontinuity, if it is not consecutive, I would put 0. But here it can be discontinuous. Here it can be discontinuous. If I have a string ABC is equal to ABC and my pattern is equal to AC, yes, it's a subsequence. I need not have a continuous string. So if AI is not equal to BJ, so AA matched, but CB did not match. But since CB did not match, I should not put 0 because if I put 0, then this C would not match in the next step.
So we'll take LCS of I plus 1 J plus 1.
LCS of
I plus 1 J plus 1.
I plus
1 J plus 1.
1 J plus 1. Should I only proceed further or there is something else? So when I'm doing I plus 1 J plus 1, you mean you are proceeding both the strings, right? So let's say if ABC was there and AC was there and I was on A and J was on this A, right? And okay, so A is matching. Let's take another, let's add one other variable. Let's I is on P, okay, and J is on A over there. Fine. So if there is a mismatch.
Yeah, only J moves.
So what should I do now?
I will stop and J will move.
I plus 1 J plus 1 means what? I'm proceeding both the things. Now let me ask you a question.
I'm just saying I will stop and J move.
I will stop and J will move. Sorry, I'm not able to hear you properly.
Yeah, I'm saying the same.
Okay. I will stop, J will move. Correct? Great. So P, A, P, C. Understand? Only this part. If you only understand this part, your recurrence is solved. You don't have to remember it. Simple. This is the change with LCW. ABC is there, AC is there. Did not match A and P. So here it is I, J. Okay. Now my question is, you say that I would remain fixed, J would move to C in order to check whether the next character is matching with this P or not. Sure. Yes, that's the correct statement. But I can also say, I can move I and check J, and I am also getting a match. Correct? So, if I keep J constant and move I, then I can get a match over here. On the other hand, let's say I just simply modify this string a little bit and say that here some, let's say B was there and here P is there. So in that case, if I move I here, I get a mismatch. B and A does not match, right? But instead of that, if I would have moved my J to P, so then I would have got my match. So in one case, if I move J forward, depending upon the strings that I have, I get a match. In the other case, if I move my I forward, I get a match. So what to do now? I have.
So, sir, for one case, we are going to I, J plus 1. For the second case, I plus 1, J will stop. Both the cases
How to choose? Exactly correct. But what should be the recurrence then?
So first we go with the J will stop and I will move. And in the second case, J will move, I will stop.
Correct.
First,
But,
yeah.
But
okay, we will take max of that.
Max or min? What do you want to do? Longest. So what should we do? Minimum or maximum?
Max.
Correct. Max only, man. You want to go for the longest common, right? So
yes.
Yeah. So simply you would apply that. Now if I go to the subsequent, sorry. Where is it written? Didn't we mention it?
Yes, it's coming. I think it's more down.
Okay, anyways, fine. So the thing is, if you see this now, so if there is a match, we would go 1 plus LCS of I plus 1 J plus 1, that is fine. But if there is not a match, okay, so either I can go in this way or I can go in this way. So the recurrence would be max of that. Wherever you are getting a longest common subsequence, you would pick up that one. Okay. So in terms of filling up these boxes, if I apply it, let's come to the boxes and then apply the same logic. Okay, what is the base case? Base case is not different. I plus 1, J plus 1, since we are doing summation. So obviously would go to M and N. Accordingly, you put obviously since there are no, at M and N, there are no leftover characters to compare. So you get 0, 0. So let me come to the matrix. Yeah. Same thing, 0, 0. I'm not discussing that again, same thing. Now let us discuss the condition. Okay, so what was the condition? If there is not a match, what I would do? I would take max of both the possible cases. Possible cases are what? I plus 1 J and J, I J plus 1. Two possibilities. If there is, so I would take max. If there is no match, no match. If there is match, I would do 1 plus I plus 1 J plus 1. That's it. I mean, all of where P is there, huh? P or whatever else, sorry, not P, LCS, 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 LCS. Fine. Anyways, so let us do that. So I would first calculate this one because that's the first number after filling up the boundary cases over here and here. Okay. So let's calculate this one. Is there a match? Yeah, there is a match. So since there is a match, what should I do? 1 plus I plus 1 J plus 1, right? So 1 plus I plus 1 J plus 1, which is this cell. So 0 plus 1 is 1. So you pick this one. Okay, so if you go to C, what would happen now? C and T are not a match, right? C and T are not a match. So what we would fill in this cell? Let us see. So C and T are not matching. If that is the case, I would consider I plus 1j and j I plus 1. Correct? So what so what are my values that I should be, which are my cells that I should be considering now? Can someone tell?
Bottom one and right one.
Bottom one and right one. So this one. What I would do? Add the maximum. Take the maximum. Correct? Max of I plus 1j or ij plus 1. Max. So which one is max? 1 is more or 0 is more? 1 is more. Put 1. So you repeat that step over here. You would get 1, 1, 1, 1. Let's take us another example where we can get a better value. So let's take this one. E with, let's say, this E. Okay, so there is a match. When there is a match, what I would do? 1 plus I plus 1 j plus 1. So 1 plus I plus, so this is the cell, right? Common cell that I'm trying to fill corresponding to this. Okay, so this is the cell. So I plus 1 j plus 1 is this one. So 1 plus 1 is 2. That's simple. Only thing is you have to see the recurrence and then you have to see what is the trend in the recurrence. Trend means, am I doing plus addition or am I doing subtraction? If I am doing addition, what would be the base case? Base case would be end of string. You apply that, fill up, and then just repeat the base case. You would be able to fill the matrix. So that was longest common subsequence. Then come to edit distance. Oh, this matrix, right? Where is edit distance? Edit distance is quite like longest common subsequence, little bit different. So the idea over here is I'm directly going to the recursive solution. If you want, you can check out the edit distance live session which we took. There we have discussed the whole problem in detail. So yeah. So see, so this condition. So edit distance, what we are trying to do is longest common subsequence. We are trying to find the longest subsequence. Edit distance means I have a string is u. I have a string u and v. Okay, and I'm trying to convert u into v. So whatever changes that I can make in u in order to convert it into v, that is what edit distance is telling you. Okay, and I want to make the least number of changes. So when I say changes, what are the changes I mean? First kind of change that you can make in A is, so if you say that there is a mismatch between, let's say, A0 and B0, there is a mismatch. So how can you solve this mismatch? My motive is to convert A into this U string into B. So I want to convert A0 into B0. So the first type of way you can do that is simply by substituting. That is, you write that A0 is equal to B0, and this is basically substitution. That you are substituting in place of A0, B0. I mean, A0, you are substituting B0. Substitution is one way. So this is substitution. Second way is you delete A0. Okay, and you proceed further to check whether the next element A1 is equal to B0 or not. So that is one possible condition. So deletion from the primary string. So all the changes that we must make on the U string, not on the V string. V would be remain constant. I would try to make change on the U string or the A1, A2, A3 to make it into the B1, B2, B2. So deleting element from A1, A2, A3 is one option. So I would delete A0 because A0 was not matching with B0, and then I would proceed to A1 to check whether A1 is matching with B0 or not. And I would repeat the same step. And the third is insertion. That okay, A0 is not matching with B0. So let me add B0 as a part of it, I mean in the U string. Okay, so I add B0. And here also I have B0, and then A0 is kept at its own position, A0, A1, whatever, dot, dot. And here it is B1, B2, dot, dot. Okay, so I add B0, and obviously my pointer was where? I mean, I was at A0, right? My I was at A0. My I was at A0, my J was at B0. So I would add the B0, I would add the, I mean, when I'm adding the character, right? So I would add it before I. So I'm adding it before my current position, which is I. I am not moving I. But now see, since I have added B0 before I, and my actual string was B, character was B0 over here, in case of the second string. So I know since I have added the common character, because I mean A0 and B0 was not matching. What is the next check that I need to do? I already know B0 has been added. So this B0 is solved. What I would do is I would keep I constant. What I would do is I would move J, because that's logical. I move J to B1 and I would compare A1 with B1. Because I already know B0 has been inserted. So this is sorted. So once this is sorted, what is the next thing to do? Oh, sorry, one mistake. Not A1. Right? I would move B1 with A0. Compare. So I know B0 has been inserted, and so that's sorted. Now next thing is I have to compare B1 with A0, whether that's the match or not. So insertion, deletion, and substitution are the three processes in which you can calculate the edit distance. All of these processes are obviously a single process. So if you substitute, that is also one work. Deleting, that is also one work. Insertion, that is also one single work that you are doing. What our concern is, see, at first it may look same, that if you are inserting something, then also you are satisfying the condition. If you are substituting or deleting, then also you are satisfying the condition. But in some cases, you would see that if you have taken decision for at a particular ij value, right, ai and bj were not matching. So what you did is you did a substitution. Rather, if you would have gone for insertion, you would see that automatically the next character is matching. So let me try to think of an example like that. So let's say A and B is over here. Okay. And here I have 1A and here I have 1A. C, and then let's say X, here Y, some string. I'm not worried about that. So this is your I starting, this is your J starting. You calculate, you check whether I and J are same. You see that, okay, it's not same. Fine. So it's not same. So what you did was you simply did a substitution. Okay. So you did a substitution and made A to be B. Okay. So A became B. Okay. And okay. So one more thing. Let me just do one more thing. So I add without substitution. Let's say if I would have added B over here. Fine, no problem. Great. Okay. So yeah, even without doing substitution, if I would have done an insertion, right? What insertion I'm talking about? Let's say, just a second. No, let me just modify. It's not the correct example that I thought of. B is there, right? Add one more A and one more B. Okay. So if I insert a B over here, it would match. It would match. Okay, great. Let's say this is also A. Fine. So okay. So let's come back to it. So A and B were the first one. So I did. It was not matching. Okay. This is A. This is A. So I say not matching. So I substituted this A with B. Okay. So I substituted it B. So how many operation I did? One operation. Substitution is one operation. Now I know that, okay, these two have matched because I've done substitution. So I check for the next character in both the strings. So I say, okay, A and A is again matching, right? So that is also fine. And then again I move forward to C and A. Now this is not a match. So up till now, if I consider up to here, what is the maximum length of match that I got? 2, right? Because this BA was the maximum length string that I had, and I got the LCS, longest common subsequence, to be 2. By doing what? I did my operation of substitution. I substituted B in place of A. Now let's revert back everything and let's come back to the previous question. A only was there. Now I see again there is a mismatch, the same thing. So initially I converted A into B. Now I take the decision, I would not convert A into B, rather I would insert B into the first statement. So I did what? I inserted B into the first statement. See what happened just by doing that. I again did one operation. One operation here also I got LCS of 2. One operation here, which is insertion. Here it was substitution. Here it is insertion. One operation I did, and it gave me what? What is the longest common subsequence now?
3.
Correct. So both the places I have one operation, but here I got LCS 2, here I got LCS 3. So by doing the same number of operations, but by doing different operation depending upon which string are you working on, you might get a larger length of common subsequence. So that's the idea. Now there is no proper algorithm to figure this out. As you can say that there is no proper, I mean, in every string it would be different, right? Depending upon the string. So what operation you do at what level you do. So that's why we do dynamic programming. And now this is the recursive structure, and what is the, let's explain that, how it is happening. So you see, we are doing 1 plus. So ET of ij means if I am at ith position in the first string and if I am at the jth position in the second string, how many operations up to the ith position in the first string I have to do in order to make it same as up the string up to the jth position in the second string. Getting the point? I want to make the first string into the second string between the I and j positions. That's right. I mean, what is the number of operation I need to do in order to make that? Okay. So you say that every time I'm adding 1, this is the recurrence relation, and these are the base cases. Base cases would come later. Let's see the recurrence first. So every time I'm adding 1. Why? Because either of you do substitution, substitution or insertion, we discussed that all these operations are a single operation. So every time I'm adding 1 plus minimum. What are we trying to do? We are, oh sorry, one mistake I did. Here we are not, sorry, I have in mind the LCS thing. This is not LCS, right? This is edit display. Sorry, my mistake. What I mean is, so it would be just the opposite. So edit distance, here also edit distance. Okay, it is not LCS. Yeah. So the thing is, here I did one operation, but I got a matching of length 2. Here I did one operation, I got a matching of length 3. So in this approach of adding, it might be the case later on, if I continue inserting, right? So I am covering up more length of the string, right? So the common subsequence over here is 3 length. Here it is 2 length. So what does this mean? If it is 3 length, I am consuming the string at a faster rate. That is, I am converting the first string into the second string at a faster rate. So I can say that if I am doing that in this case, that means my edit distance is less over here, because I am doing a single operation to convert a larger part of the first string, which is 3, into the second string. Here again, I do a single operation only, but my common is only 2, right? So that means I am trying to minimize the number of operations I need to do in order to convert the first string into the second string. Okay, so that's the whole idea. I want to minimum. With the here I have taken the example of same number of operations, but the length of the string that you cover is where less and where it is more. You can also see this problem just from the other perspective, that if you keep the length same, if you keep this ED as same, right? if I keep this length same, let's say I say that you have to match till C. Then in the first case of substitution, what you had to do? You had to again do one more operation to do a substitution to match A with C. Getting the point? So there it would be two operations. So either way you can think, if you are keeping the length fixed, then you have to do more operations. That's the idea. So basically our main motive is I want to reduce the number of operations. So that's why I have written the main over here. And these three possible cases are because of the three possible operations that is available at my arsenal. I can apply either of them, but I don't know which one would exhaust the whole string at a faster rate with lesser number of operations. So I do these three. Now, how this I plus 1, j plus 1, all these are comprehended with respect to each of the operation. Let's see that. Fine. So what is this ed of I plus 1, j plus 1 mean? See, when I do a substitution, what I do? I have A, B, C, I have B, C, A. If I substitute this A to be B, what is the next step that I would do? I am already knowing that these two have already matched because I have substituted, right? There is no question of anything else. So these two have already matched means what? I would check the next of both the things. So I would check over here, I would check over here. So this is I plus 1, j plus 1. So substitution is corresponded to I plus 1, j plus 1. Okay. Now, what is this ed of I plus 1, comma j? Here I am only increasing the I. So let's say this is I and this is j. So I'm only increasing the I. When did we increase the I? Remember what did I discuss while discussing subtraction and addition?
When we delete from U.
Here it was A, right? Yeah. This is I, this is J. So when I increase the I, that means I have deleted one element from here, right? So you do that. And when I'm increasing the J, that means what? My B, I have already inserted one B over here, right? So I'm not bothered about this B anymore because I know that I have inserted one B over here in the left hand side and I is over here. Yeah. Okay. So I'm not bothered about this B anymore because I know I have inserted one on the left hand side of I. What I'm bothered about is whether the next character in the second string, which is C, whether now that is equal to I or not. Okay. So I increase the J and I keep I constant at A. So when you are inserting, this is the case. When I am deleting, this is the case. When I am substituting, I am increasing both of them. Okay. Simply take an example of like the example that I took. If you have understood it, it's fine. If you want to again just do it on your own, take an arbitrary string and try to think what you would do. But insertion is always happening on the left hand side of I. That is one point. Do not think that if A, B, C is there, I is over here, so you would insert B here. No, I mean, then you are neglecting this A. What happened to this A? Because you would proceed further from here. That's not the point. Point is, wherever I is, left hand side to that, you would always do the insertion. Okay, so that's the only one. After that, you can just do this recursion. Okay, so just apply it. Base case is again, we are doing plus simple. Base case idea is same. If you are adding it up, then you are going to the M, right? So you have to go to the M and N, I mean the boundary cases. And then you have to think accordingly, what is my boundary? So when I reach the boundary, again it is 0. But the thing is, one important point of difference is here in case of edit distance. That difference is this second part of base case. So in some subsequence, when we had at least any one of the string had come to the end, we knew that there is nothing common to be matched. And that's why it would be 0, because longest common subsequence, it should be common. If there is at least one string which has reached its end, then there is no character left in that string, and therefore there is no common thing coming up. But here, if I reach both the strings end, then that is fine. I mean, I have nothing to do. But if I reach one of the strings end, let's say I is there, but I have reached end. I mean, for the J, I have reached the end. Then what does that mean? That is, I have, let's say A, B, C, D, dot, whatever, up to let's say this is M length. and here I have B, C, A, dot, 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 whatever, up to n length. Okay, and let's say I is over here, so I is between somewhere else, in between, but J has reached n, right? So J has reached n. J is pointing over here. So what does this mean? That I am considering n, this last character, n is the length, right? So let's say the nth character is over here, let's say it is some x. Okay, and here the last character is something, let's say p. So when I have reached the nth character, which is x in J, so what does it mean? That I would compare this with the ith character. Okay, and what would happen after that iteration? That is when I have exhausted the whole string. That is, I have actually crossed n. I have gone to the, so basically the index starts from 0 to n, right? So since it is starting from 0, if I consider n is actually past the string, because the string would be 0 to n minus 1. So x is at actually n minus 1. Fine. So but when I've reached n, that means I have exhausted one string. And that means if I want to convert the first string into the second string, what does, I just want someone of you to tell me that.
We already have converted, that's what it means, right? The first string.
No, we have
delete
not
the balance ones from.
delete the balance, because I have not yet reached the end of this string. I am in the middle, but I have actually converted the
No,
second
what I
string.
meant is we have converted at the point of I. We already converted the first
Then you are
string.
correct. Yes,
Yeah.
yes, exactly. Exactly, that's the point.
Then we go for deletion. Yeah.
Exactly. So we delete this part, whatever is there. So that means what? How many is left over here? If my length is m and I have reached up to I, so m minus I. Accordingly, if I have, what would be the other base case? If this is 1 comma I comma n, I would also have a base case which would be there in the next slide, possibly. That base case would be what? The other thing, which is ed of
m comma j.
M comma j. In that case, what would be it? That I have reached the end of the first string and my next string is still left. But
can you repeat? I didn't
what would be the other base case? If I and j both are increasing in the recursion, right? I plus 1 is also there, j plus 1 is also there. So both
if that first string is got over, okay.
So the first string is now over, second string is still left. What I want to do is I want to convert the first string is over and second string is in the middle.
Insertion.
So I want to convert the first string into second string. So I have to insert the balance amount of character which is there in the second string into the first string. So here it is deletion. M minus I deletions. Here it is n minus j, because the second string is at j position and my length is n minus j insertions. Questions? There is a high probability that from this topic, one question might come, which is asking you which is related to the interpretation of these operations and this thing that I just discussed. If you understand, I would not be able to tell you how that might come, but if you understand whatever we discussed just now completely, why I plus 1, why j plus 1, why I, why j, then you should be able to answer that question. After that, I'm not going into the matrix because just the repetition of the same thing. You go to the base case and simply fill according to the recurrence that we just discussed. Find the minimum of I plus 1, j plus 1, ij. So in this case, what are the, so if I say, let's say this is my matrix, okay, and this is the cell I'm considering to be filled. So what are the nodes that I would require in order to fill it? At first, I would require this one,
the diagonal one, and then the left.
Correct. So I would need all of them. It is I plus 1. So I plus 1 would be this one. We are increasing I, and j is constant. So basically, I plus 1, j is constant, right? Yeah. This is 5 plus 1, and my j is constant, and the other one is I is constant and j is increasing, which is this one. So these three cells I need, and then I would find the minimum among all of these three, whichever is the minimum, I would pick that up. Okay, if there is a mismatch. Okay, but if there is a match, that means A, B, C, A, B, C. How many operations do I need to convert it into this one? 0 operations, correct? And let's say if I A, B, C, and I have A, B, D, then A match. Do I need any operation to do? No. I would proceed further. B match. Do I need any operation? No. Proceed further. Here I would need one operation, only one operation. So whenever I had a match in edit distance, then I obviously it's opposite to LCS. LCS, when there is a match, I would say that my length of common word is increased by 1. I got a match. Here, whenever I match, I do not need to make any change. I do not need to edit something. So that means I do not have to add anything. So whenever there is a match, we do not go for anything. We just move to the next cell to check for the equality of the next cell. So you see here, if there is a match, I'm not adding 1 plus or anything. Right? I'm not adding anything. I'm just moving to the next cell. Okay. But if there is not a match, then I'm doing one operation depending upon which one. So if you go to the matrix, just let me just mention it briefly. So what you would do, the 3 orange cell that you just drew, you would just find the minimum value among those 3 orange cell and place it on the top if there is a mismatch. And if there is a mismatch, then you would simply put the value which is there in the next cell. So let us take this one, E and E. Is there a match? Yeah, it's a match. What I would do, just put the value which is in the next cell. If I'm solving for this one, right? What I would do, just put the value which is in the next cell. Put the value over here, directly copy paste 1. If there is a mismatch, take this one. Okay, so this is a S and E. What I would do, find the minimum among the ones that we drew, I mean, these 3, right? These 3. I mean, you have to check that. I mean, if there is a just a second. 1 plus the minimum, right? Yeah. So you find the minimum and then you add 1 plus. So which one is the minimum over here? 1 is the minimum. So that means what? In order to reach this particular position, right? So this particular position, E match, I needed to do one operation. And in order to again have a S over here compared with the same up to the same level, I need to do one more operation, right? So that is 1 plus 1, which is 2. So basically you pick the minimum among the 3 and then you add 1 with that, like that, just the recurrence, same thing. But now I picked up 1 from here, correct? Because that's the minimum, and I added 1 and placed it over here, which is 2. Can you tell me what operation I did?
So where?
Sorry?
Can you repeat, sir?
So I have to pick the minimum among these 3, and then according to the recurrence, I would add 1 for the operation that I did, right? I would add 1 corresponding to that operation and place it over here. So I picked up 1, I added 1, that is 2, and that's why it is 2. But my question is, in order to come at this cell, from this cell, what is the operation that I did? Did I do insertion, deletion,
Insertion.
Insertion, because it's I plus 1, right?
Yeah. So this question might come again. I am just discussing all the types of questions that might come, so that it should be helpful for you. That we might give a matrix, we may not give you the recurrence in that case, right? But the problem statement would be given, and we might ask you that if this value is 4, and let's say these 3 values are as it is given over here, right? We might not even need to give you the full matrix. Just this part we give. And if this is 4, okay, these 4 values are given. What is the operation that's done? That is one possible question. Okay.
One doubt here, numbers are same, right? How can we say that? Because he could have picked either diagonal or
Sorry. What are you saying?
Here, the numbers are same, right? We could have picked 3 or this 3, right?
So yeah, so numbers are same. First of all, you just let's do it sequentially only. First let's check. First, let's check whether there is a match or not. This one.
So this entire matrix will be given as a image.
Yeah. If it is coming in that manner, if we are asking, then it would be given. If we are asking the recurrence, it would be given. Okay. Okay. So let's discuss this. So 4, this cell I want to check, and I see here B is there, and here R is there. It's a mismatch. Correct. So it's a mismatch means then I would check the minimum value among all these 3. So this one, and this one, and then add one. Now you are saying I can see that both of these are 3. So that's why both of them are probable answers. You can pick either one of them and say +1 is 4. The difference is if it comes in the question and ask which operation can you do, then it would be an MSQ. Okay, it would be an MSQ. The question would be which operation to do if you want to have a minimum possible edit distance. So you can either do addition or you can do substitution. Both of them suffice.
Okay, thanks.
Yeah. So both of them in this case would give you the would convert the first string into the second string by doing the same number of operations. Okay. So that's done. Edit distance is completed. Matrix multiplication. So this one I remember I have discussed it in very detailed in the first in the session matrix multiplication, and I have discussed in continuously for 2 sessions. So if you have any specific doubt with respect to matrix multiplication, you can ask, or otherwise I would ask you to actually check that session. I mean, I have discussed it from how many possible associative structures can be there, how you can do the multiplication by drawing the matrix, filling up the matrix, all those things we have discussed. If there is any specific doubt, you may go ahead and ask. Otherwise,
I think I have watched that video.
Yeah, I would request you to do that, and if there is further doubt, then you can post on Discord and tag me. Okay. I would answer. So I don't think you would have any doubt because that's discussed in more than required manner. So we have also discussed the number of associative structures that are possible and all this. Anyways, check that video, and yeah, I hope that should be okay. Okay, so that's done. And yeah, you want to ask something?
No, sir. Okay.
Okay, great. So only one thing is left, that is the week 9 concept, that matching algorithms. So I would give a suggestion on that because it's 12 o'clock and 10 people are there. Week 9 concept, the suggestion is learn the complexity parts. Okay, because see, it's a matching algorithm. So we cannot ask you any question depending upon, I mean, what is this value, what is that value? Everything is based upon the programming. I mean, how you can gain the complexity by applying a better approach, right? So week 9 problems would come mostly in a way of statements of, let's say, KMP algorithm. What is the complexity for that, right? Or it may come in a bit more complex statement that what is the advantage that I mean, choose the correct option from the following, and it is saying that the best case complexity of KMP algorithm is this. The best case complexity of the worst case complexity of Rabin curve is this, like that. Okay, so read those things, and again I would ask you to do the same thing because we are not discussing any really specific problems from the string matching part. If there is some conceptual doubt, please post it on Discord, tag me, I would answer. Okay, and if there is any doubt, you can ask as of now in the string matching. If you have specific doubts in any of the string matching algorithms.
No, sir. I mean, if the problem comes like find the number of iterations, then it will be really lengthy question.
No. Number of iteration would not come in that manner.
Then it's fine. I mean, then it is only the remembering part, complexity and all.
Yeah, for the time being remembering, but I mean, you would have to code it up. I mean, now the course is over from that sense, but in real life, you have to do a lot of string matching coding if you are making tries and all those things. So I would request you to understand the algorithm. Just don't for the exam sake, see the complexities, but please understand those algorithms. They are very important. Okay.
Yes, sir.
Fine. So, okay. So that would be it for today. Is there any doubt on any topic?
No, sir.
No, sir. Thank you.
Great. Okay. So it's late also, but if anyone of you has any doubt in any topic, tag me in Discord. I would try to answer.
I just have only one doubt in time complexity.
Yeah, please.
It was given in the actually revision sheet, but I didn't get it. It was 3t of n by 3.
Just a second. Is it a recurrence?
Yeah.
Acha, t of n equal to
3 into t of n by 3.
Okay.
Plus order of n.
Okay.
It was matched with the order of n log n that I couldn't understand, because each step we are getting order of n. How n plus n plus n plus could be added to log n? That was I didn't get it.
Okay, so you can just solve it and check. So let's try to do that. So I have 3t by 3. So t of, let's say I have n by 3, right? So I'm just apply the recursive structure. So let's say 3 square. Okay, sorry, not 3 square, 3 equal to 3t. Now in place of, obviously, okay, so 3 t of n by 3 square plus, now my itself is n by 3. Okay, and yeah, that's it, plus n. So what is it becoming? 3 square into t into n by 3 square plus n plus n. Okay, great.
Okay.
Fine. Next, let's see what is the next step. 3 square into t of n by 3 cube plus n by 3 square, right? Plus n plus n. Did I do this multiplication correctly? Yeah. So what is this? 3 square t of
1 3 is missing.
Yeah, thanks for that. Plus again n plus n plus n plus dot dot dot. So basically this is becoming 3 to the power k t n to the power 3 to the power k plus n plus dot dot dot. How many times I'm doing it? In 3 it is k times. Correct?
Yeah.
Fine. So okay, so n to the power 3 to the power k at the base case, n by 3 to the power k must be equal to 1 as my base case, right? And t of 1 would be a constant. And that time, what would be n? 3 to the power k. Logically, if you apply log n base 3, but basically it's log n. So k is log n. So I get 3 to the power log base 3n plus n time, I mean log n times n plus n plus n plus, how many times? K is log n, correct?
Yeah.
Log n times. So if you are doing summation of n log n times, that is n log n.
Okay. Yeah.
Right? And what is this part? Let us solve this as well. We know that according to the properties of logarithm, if I have some base a to the power log a n, that is essentially n.
N. Yeah.
So this is n. So I get n plus n log n. Obviously, is the more greater factor, so that's the complexity.
Okay. Thank you. Thank you very much. Yeah.
Okay. Fine. So thank you all. All the best for your exam. Yeah.
Thank you, sir.
Thank you very
Great.
much. Sir.
Great.
You did a
Thank
very
you,
good
sir.
job. Thanks a lot.
No. Thanks. Good night.
Nice, sir.